but I just told Lee to go live. Yeah, so you can stay here.
All right, we are going to get started for the first ever Open Healthware Conference. This is a super exciting day for OSHWA and hopefully for all of you as well. I just want to welcome you here in this room. I also want to welcome all of the virtual attendees who are out watching this live stream. And I want to give a special welcome to all of those who got their flights canceled last night or this morning trying to come into, I think we had looked up LaGuardia at one point, was just all red with canceled flights. So welcome to those folks as well who I know were planning on being here and couldn't due to the rain. So as I said, this is our first ever Open Healthware Conference. This is super exciting. I am Alicia Seidel. I'm the Executive Director of the Open Source Hardware Association. We have been around for about 14 years at this point, which is kind of crazy and exciting. So let me tell you a little bit about OSHWA and how we got here. So what on earth is the Open Source Hardware Association? We are stewards of the definition of open source hardware. We didn't write the definition, the community wrote the definition, and they did an awesome job. And so we just put it out there in the world and help people understand what it means. We're also the umbrella or standards organization for open source hardware. So we just kind of double check that people are adhering to open principles. We're the certification holder. So that means that we certify open hardware projects and we kind of verify and double check that all the information's there. We also, through the certification, we get to collect data on our community, which is pretty fantastic because we get to see how the community has grown. And we also clearly, as you are here, organize community events. So what is open source hardware? Just so we're all on the same page, I know you all already know this, but open source hardware is hardware in which you can remix, remake, remanufacture, redistribute, resell, or study and learn from that hardware. If you do open source hardware, you are more than welcome to use this community logo right here. It's like a little gear shape. And that signals to the rest of the world that you are doing open source hardware and that they are allowed to resell your project. They are allowed to study and learn from it all the way down. They're allowed to remix and remake. Okay, so what am I exactly talking about with source? It is anything that somebody else would need to make a copy, right? That is the ultimate test, is can somebody else replicate this? If the answer is yes, then congrats, you have successfully done open source hardware. So what this means is things like schematics or CAD files, even hand drawings. We have an open source hardware hammock. So sometimes it's like fabric, sewing, designs. Any of the things that are up here are all copyrightable, okay? So in order for open source to exist, we need the laws that are couched in intellectual property like copyright and patents so that we can create an alternative for those laws. So the example I have up here is the University of Wisconsin open source face shield, right? So this is one of their diagrams. Yes, you can see that you need bow form, an elastic headband, and a clear shield, and then they go into like, you know, the laser cut designs for this thing. And all the specifications and measurements that you would need. All right, and so then if you have created open source hardware and you want to get it certified, we don't force anybody to get certified, but if you want to, we have a certification and that creates this awesome database of all the different things in there. And that really allows us to collect that data that I was talking about. We have over 3,000 projects in our certification database. And like I said, you don't have to, but some of the benefits, if you are, is that you get attribution, and then within the certification, we actually ask if there's a line item that you need for citation. You also get access to, well, everybody gets access to CERN's open hardware licenses. But I think this is like, I like to point out that like CERN has created a bunch of open source licenses, like Large Hadron Collider CERN, right? Like Switzerland CERN, right? Like that CERN, like CERN, right? Huge scientific community, big project. CERN's not going away anytime soon. And they're the ones that created these licenses. And so that is really important and really exciting, that they are the people who are creating the licenses. So we also, the certification and open hardware in general gives you provenance, but the certification enables you to be part of a directory. And so people can find your project there easier. It encourages community collaboration. It creates prior art, which again, couched in copyright law, prior art is incredibly important for everywhere in the world creating open hardware. It also incentivizes innovation. And the certification specifically has, this third-party validation and verification effect, right? So we actually check over the files. We make sure that they're all there. We make sure that they're all licensed properly, right? And we'll let you know, like, hey, oops, you forgot to license your code. And when you forget to license your code, it automatically goes into copyright instead of having an open license on it. So we'll let you know if it's not licensed properly, if all your source isn't there, we're pretty nice about it. And so this is really what open source hardware does, and the open source hardware certification does for you. So when you think about OSHWA, you can kind of think about us in the way in which we are an alternative to copyright and patent, right? The world that we live in is intellectual property. We are an alternative to the US Patent and Trade Office because we are a US nonprofit. However, wherever you are in the world, you also most likely have a patent and trade office. So it functions the same internationally as it does here. So we do try to take care of everyone globally. And in the certification, you also get a country code so that we also can kind of gather that information as well. All right. Okay, so why are we doing this whole open healthware thing? So we started noticing people were emailing us and being like, hey, your certification doesn't have like health or bio or medical category. What's up with that? And we honestly thought those people would never be interested in certifying as open source hardware. And this makes it tricky to get that data without that category there specifically. But we have 79 current health items that we could find, right? We might be missing some because, again, without the category that people have been self-selecting, we kind of had to do some digging. And 75% of those are in the database are for humanitarian aid. So I thought that was kind of an interesting thing to pull out, that a lot of the people doing open healthware are doing it for distributed manufacturing so that somebody else can quickly make a copy and utilize it for humanitarian aid. So we were curious, and I know our team has pulled out kind of all the interesting parts to them that they have heard from our community so far. So we've had these workshops with participants, and our participants have told us, hey, in the source, it's really important that the sterilization plan is included. It's really important that there are device legacy plans. So when a company goes out of business, we know what the plan was with that legacy. Really important to have testing docs and regulatory files within their source. And then there's also like these really fascinating things I've learned about historical sort of non-patent points, right? So generics, think about generics, right? We already have a map to open source within medical with generic drugs. These are drugs that just don't have their patent on them anymore, right? They have gone out of the 17-year mark for patents. Seatbelts are another one. Seatbelts. I mean, not specifically maybe how we would think of a medical device, but certainly safety, things that help human health. They recognized that was so important and so life-saving. They said anybody can use this patent. This is too important. Insulin in Canada, that patent was sold for $1 so that anybody could have access to it. Unfortunately, here in the US, we have sort of, a different, concept around that. So we have some repeated strong justifications the most important one of these, I think, is that people do not want us to be the FDA, and whew, thank goodness, because again, we are tied a little more to IP and not at all to health and safety and efficacy within that. So we do not want to be the FDA. We know that all the open healthware should go through a regulatory body if it needs to. Our stakeholders have told us this repeatedly. And also, interesting point, open and closed business models seem to be incredibly similar for health hardware. All right, so we want to recognize that IP is not about quality. So this is my garbage can, and we live in a place where there's bears. No bear has ever attacked this garbage can. However, this patent pending up there, right? This is the third time that we've had to replace our garbage can this year because it just falls off all the time, right? So not about quality, mapped to the healthcare industry. We also understand like insulin, right? There are 2 companies that have patents on insulin. And what happens is we have people doing protests in this country over die-ins because people cannot purchase their insulin because insulin prices are too high. Pulse oximeters do not work on people with darker skin, right? How much data are we just sort of letting go or doing wrong because these devices were never meant to work with certain people or because patents have stood in the way of cheap enough medicine? So again, we want to recognize that patents are not about quality. The USPTO does not give a patent based on quality. But there is hope. Just want to run through a few examples. Field Ready is an amazing organization, another nonprofit that does humanitarian aid devices all over the world, all open source hardware. Open source hardware medical supplies is a fantastic database, all open source hardware items in here. These are all gowns that I pulled, hospital gowns. Ubora is an international group that also has a database for biomedical engineering. And Glia is an open hardware business that is selling these items currently out of Canada. And so, with, social media splintering and whatnot, like here's all of our social media now. So take a picture of these QR codes. They'll also be up at the end. And then I need everybody to take your phones out right now. These aren't the super important ones, but you can, of course, follow us on social media. But are you guys ready? Is everybody ready? Okay. Oh, thank you for the dermal. All right, we have a survey that we really want everybody to take. We'll be bugging you with this all day long, we promise. This is our survey. This is kind of a culmination of the first 3 workshops that we have done and the data that we have collected from them. But we really want folks to take this survey because this is like sort of, here's the data we found from participants, and now we want to make sure that that data is correct across, the rest of the participants who haven't attended our meetings and across the globe. So that is our survey. Thank you all for taking pictures of that. And I just want to say this work is financially supported by the National Science Foundation, so thank you very much to them for the finances. But this work is emotionally supported by you all. And so thank you all so much for being here. Thank you for being a part of this community. We're super excited to work with you and to build with you. And so that is the end of my presentation. And I want to introduce my esteemed colleagues, Dr. Avinash Bhaskaran and Dr. Eve Nazan, both recent postdocs. Yes, come on up to the stage. So we are fortunate enough to have these 2 gentlemen working with us at OSHWA. Our grant has them here as part-time, so they are hireable. And in a year, we're hoping to keep them on if we've got funding, but you all know how this world works. So I'm going to let them introduce themselves, but just know they're looking for work.
Thank you, Alicia. Appreciate it. Let's put it here.
Yeah. Thanks.
Oh, JK.
Oh, they clicked the yeah. That looks right. You want to switch it to extend screen or something?
We weren't going to do presenter notes.
Okay, what do you think?
This one.
All right. Yeah. How many engineers does it take to start a presentation?
At least more than two. We have phenomenal tech support right here, so we're working out.
Okay, thank you very much. And thank you all for being here. You know, we're really grateful to have you all. You know, Eve and I are postdocs and we're somewhat new and into our career. So I actually graduated in the spring, so really new. And just really grateful to be able to share with you guys the time and your perspectives. Just hoping to hear from the presenters and hope to present something useful today here in our time. So my name is Avinash. I have my bachelor's in biomedical engineering, master's and PhD in mechanical engineering. So during my PhD for 3 years, I was a NASA fellow, so developing exoskeleton control technologies to improve the health and safety of astronauts. And so following that experience, I joined OSHWA as a part-time postdoctoral fellow. And I've also started a couple of interesting organizations kind of around the ideas of open source. So I started, you know, a little bit of the story is I turned down some more lucrative job offers to move to rural Alabama in an unincorporated part of the country to start the Precision Agronomy Research Center. And the idea behind PARC is there are a lot of cool open healthware technologies that are still struggling from the need to network, to generate test data, independent validation. And so at PARC, I'm working with a couple of funding partners to pilot open source technologies with the applications towards rural resilience and health and medical applications where supply chain is constrained. So I'm working with Open Source Ecology to develop an autonomous version of their open source tractor. I'm working with Public Invention and Open Flexure Microscope to actually model biological samples from farm animals. And so that's something I want to talk to people here about is third-party validation with animal models. I'm definitely interested in working with you guys. And I'm also working with Auburn University in the state of Alabama to help teach and mentor from the K through 12 level all the way to veterinary medicine and clinical students at Auburn University. And so starting to try and get open source into the hands of clinicians and develop the education and the language and the literacy around open source so that as the healthcare community matures, there are trained clinicians and vet med professionals who can embrace that technology. And so on the for-profit side, I guess not really for-profit, but I'm not profiting yet, but human labs. So the idea is there are people who want to use open source who either have a hard time selecting devices or sourcing them or how to manufacture them. So specifically an application with K through 12 teachers, especially in the rural areas where they just don't have necessarily the literacy or supply chain to get these materials and to maintain open source materials. So I'm working with teachers in 5 states. And in Alabama alone, 3 different high schools, over 1,000 kids that are seen every day by the program to basically find open source technologies that are related to EdTech or can be applied to EdTech. For example, Open Flexure Microscope, and to manufacture them, sometimes on a contract manufacturing basis, distribute them, develop curriculum around them, and support and maintain those and to provide assistance there. So this is as close as I'm getting to a business card right now because it's just, I graduated in the spring. So if you would take a picture or just remember my name and it's at oshwa.org, shoot me an email if you're interested in talking, learning. The main thing I need right now desperately is guidance, advice, and just a wealth of wisdom and how to proceed. So again, grateful for you guys to be here and share your time with us, and I'll hand it over.
Thank you, Dr. Bhaskaran. So my name is Dr. Imezo II, and so all my degrees are in mechanical engineering. I graduated from the University of Michigan, go blue. Go blue. Love to see it. So currently, I am a policy researcher here at OSHWA, but also I am a mechatronics fellow at Walter Reed National Military Center right outside of DC. I work in a lab where we look at soldiers who have amputation and look at how can we better their quality of life? How do we monitor what the quality of life looks like after different and varying forms of amputation? I specialize in making test systems and making devices, which is also a thing that I do separate from this. I'm also an engineer and consultant, so I have colleagues that I work with from NASA, George Mason University, and Johns Hopkins University, where we specialize in mechatronics or electromechanical systems and building and designing those things. So if you're interested in that, please, I'll be around all weekend and love to talk to you about that. But thanks. Now that you've heard about us, let's tell you about what we've been doing. So I'm going to go take you briefly through a roadmap of what we've done and talk about where we're planning to go. So as Alicia's already done so phenomenally, we learned a lot during our times during COVID. And then so during COVID is during those times that we learned actually, okay, maybe there might be something here with this Healthware idea or doing something with open source medical devices. And so from that, we applied to funding. We tied some initial interviews that really informed a series of workshops that we performed. So many of you actually were there, and these were virtual workshops that we performed to get a better understanding of what it is that our community wanted and what it is that our community needed. And so from these virtual workshops, we were able to then really hone in on some key questions and then figure out in some in-person workshops what are specific questions that members of our community really care about. And so it was from that we pulled 4 key themes from all of this data and all of these interviews and workshops that we have been performing. And then after talking about those 4 themes, we'll talk about some of the future directions. So I'll start with COVID. Before COVID, as Alicia pointed out, there were, we now currently have 79 health or medical related devices that are certified on OSHWA. Before COVID, we had 1. So that means 78 before COVID. And that was really because we had little to no concept of what it meant to have a medical certification, right? We certified open hardware devices, and that seemed sufficient at the time. But it was during COVID where we really saw that quick access to medical equipment like PPE, ventilators was incredibly important. Some examples of this were at the University of Wisconsin. They made an open source face mask that was actually adopted by Ford Motor Company and then made in the millions. Another example of this is a medical device manufacturer called Medtronic. They open sourced their designs for ventilators and made that available to all people due to the need that was seen during COVID. And so after COVID, there are 2 things that really came out that we saw as OSHWA that were needed. So the first was that we had notable and numerous requests for a medical certification that really answered, or a type of certification that answered the question, what does it mean to both be open source and a medical and or health device? And then the second thing we saw was that there were a lot of people who were doing phenomenal work, both individuals as well as organizations, but a lot of these things were disparate and not connected. And so people needed a way to direct them to the organizations or projects that they needed. And so from this, we started what I like to call our Healthware journey. So we thought the best way to do this would be to create an ecosystem, right, that can connect all the people and players that are necessary within this open source medical device system. And we figured it would be much easier to direct everybody if they were connected. So to do this, we applied for an NSF POSE grant, which we got. And we also created this term Healthware, which you'll hear very frequently this weekend. And so Healthware was supposed to be a unifying idea to bring together people who considered medical devices separate from healthcare devices, saying that they didn't really have any overlap. An example of what this might look like is that you could have something that's open source, like a pacemaker, but you also could have something that is, the equivalent of an Apple Watch, or maybe like a sensor ring, like an Oura ring. And both of those things, right, have medical or health-related applications, but there are very different things that are necessary to make these things happen. And so we wanted to understand this question about what is required to make an open source Healthware certification, or what is really necessary to make something like that. And so we started off by doing 100+ interviews, and we had some pretty interesting things that we found, at least at our first go. So the first is that if we were to go through with the certification, we're going to need to accommodate a wide variety of needs, right? The US is not the only place here, and so understand there are a wide amount of global needs. There are a wide amount of needs for people who have different regulatory considerations, and so that was something that was important. We also found that certification users valued very transparent and equitable healthcare solutions. Keeping that in mind will be important for future success of the certification. We know that people don't want to do harm, but people are scared of getting sued. And so making sure that we can do something that can both inform people about liability, as well as making sure that the intent of what people are trying to do with their open source devices can be conveyed will be important in the future. And last but not least, we also saw that threat modeling will be important for standards organizations such as the ISO, the FDA, or local regulatory boards to make sure that they are on board and that whatever we create is not competing with, but is actually compatible with the things that these regulatory bodies create. And so these original interviews set us and led us to a virtual workshop, three sets of virtual workshops, and helped inform those. And so we had some key points that we figured out during these. First and foremost, we as OSHWA are always trying to move where our community takes us. The first thing that we heard loud and clear was that the community does indeed want a Healthware certification or something like it. There are people that referred to it specifically as a certification. There are people who referred to a set of norms or practices or standards, but it was a common theme that we heard frequently, and that was encouraging to let us know that we were on the right track. We also were started to identify key stakeholders in this ecosystem that we're hoping to create. So some of these stakeholders might be makers of open healthware devices, people who replicate open healthware devices, clinicians, regulatory bodies, and more. We found certain things that we can already have early on as marks of a successful certification, two of which being this certification will need to align well with whatever your local regulatory board is across the world. So that might be Health Canada if you're in Canada, FDA, what have you. And so we also found that to make a certification, we'll know that it's a good certification because the devices that we are certifying will be well documented and replicable. So we also found that there needs to be somebody, right, that oversees this. And so this certifying body should verify transparency, but not guarantee safety. Alicia already said that we don't want to be the FDA. And so that's important for us to make sure that we're saying that this is truly open, but leaving the guarantees of safety to others. We also found that trust is a very important thing in this equation. So people are going to need to trust the devices that they are trying to build. And so how do we do that, right? How do we build this trust? But lastly, from the virtual workshops, we learned that however we define healthware in a formal sense, should make sure that it emphasizes the importance of good documentation as well as safety in some way, even though that we as OSHWA are not saying that we okay safety. And so from that information, we then got to dig deeper in some of the questions that came out of the virtual workshop and turn them into 2 in-person workshops. And so from here, we saw that we need to manage this interesting triumvirate of risk, safety, and trust. And so we needed to figure out, okay, we understand that we want to mitigate risk, right? But we can't guarantee safety. And what is the interplay of these 3 ideas? We also found that people, at least for the initial iteration of what this healthware idea is going to look like, are interested in OSHWA being the governing body, which is cool and a good thing to know as we move forward. But we also want to keep in mind rather that there will be other iterations of a governing body, right? And so making sure that OSHWA can start there, but we make sure that we create something sustainable that may or may not revolve around OSHWA being a governing body. We saw that clarity is key. So many things, people want to know what they're certifying, why they're certifying, what the certification does for them and does not do for them. And so things that are also going to be important, right, is understanding what OSHWA's role is, as well as understanding the limitations of devices that are certified. We also saw that the certification is going to really need to be inclusive to diverse needs. So we really got to hone in a little bit more about what's going to be important for particularly our global participants or maybe our non-Western participants. What do they look for in open source devices that make them useful for them, and make sure that we include that when we're thinking about a certification. And then lastly, people want community. And we know that OSHWA, here at OSHWA, community is really what drives things. And so our community can be great for anything from implementing projects to making sure that the ecosystem both sustains itself and grows, as well as the people swapping knowledge, being able to swap resources and all of that. And so making sure that whatever our certification does is inclusive of people and builds community and not takes it away will be something that's really important for the future. And so from all these workshops, right, there are 4 key themes that really appeared. And so the first of which is documentation. Now, what makes documentation important is that people refer to documentation, but they actually have been using that as a proxy for other ideas. So one of the ideas is that when people talk about, oh, documentation is very important, what they're really referring to is this idea of something being safe or having trust in a device. And so one thing that we learned is V&V testing, also known as validation and verification testing, is going to be really important to actually have people trust the devices that they plan on using. One thing that was actually even doubled down on that was third-party testing, right? So it's one thing to have the maker of the device potentially provide documentation that says this device is supposed to work in a certain way, but we found actually third-party testing, right, even bolsters that trust and bolsters that feelings of safety even more. We also found that the better documented that a project is, right, the more safe and the more trust that people have in it. We also found that sometimes when people are talking about documentation, what they're really asking for is ways to connect with different communities or communities that they find to be disparate. So one thing that we found is documentation definitely needs to be culturally adept. So an example of this could be if our certification is able to be seen in multiple languages, or if you have a certification that's both applicable here in the US and maybe somewhere in sub-Saharan Africa and also maybe somewhere in Thailand, right? Making sure that the certification that we create is applicable in multiple environments, multiple regions. We also found that one way of building community that was brought up before is that people are looking to OSHWA to direct them to other places that they have to go. There are plenty of people who have the ability to build and create things, but they need to know, well, if I have part A of an open source device, or maybe if I want to make some tweaks, where do I go to either find the base, or where do I go to find people who are knowledgeable in that? And so having good documentation about who even exists in the space, we found to be incredibly important. We also found specifically for projects, when people talked about documentation, what they really meant is transparency. So they mean, if I find a project, you want to have transparency in that. And so with that, we found that better documentation is going to be something that people kind of desire as a new norm. The current documentation that's held for, new norm. Current documentation that's held for current hardware is actually, we want to bolster that with what we have here for hardware or for healthware. So briefly, I'll go over this term that we're calling globality, which is really just thinking about what are the global implications of the hardware and of the certification process that we create. And so there are cultural barriers to adoption, and it's just going to be important to keep that in mind. There are places that have fraud. There are places that have different cultural norms. One of our participants said, and I'm paraphrasing, the US is the only place where people can actually pay elected officials to do something, and it's called lobbying, not corruption. And I think that really underscores, okay, depending on where you are, it depends on the rules of engagement. And so we know that people want a governance body. We know that people kind of want to be connected at local hubs. And so we want to make sure that these are things that we account for as we move forward. Quickly, I'll talk about just the idea is like, we need better marketing. People think that open source can mean cheap, and we want to make sure that people understand low cost does not mean low quality. And so just better educating people about what is open source healthware, and how it can be useful is something that will be important for inspiring confidence in the future. Lastly, the idea of reproducibility is something that's very key. And so the points that you're seeing up here are points that I've already talked about, but we have found that when we look at these specific questions through the idea of reproducing something as opposed to being a creator, the outcomes that come from that are going to be very different, and that's going to be important. And so with that, I will pass to Avinash.
Thank you very much. Thank you, Eve, for introducing us to the conversations we've been having with our workshop participants and our interviewees and people we've been talking to in the community. And that's a big part of our year one effort, is just trying to understand and capture and image the community that we have here and all over the world. And so up here are, so what I did is I went through all of the Post-it notes that we wrote on walls, all of the Word documents, typing in bullets, and there's thousands of data points. So if you thought you didn't know and read what you wrote, someone read it. and wrote down kind of what you were thinking on an Excel spreadsheet and labeled them with some data labels I'll talk about. So on your left side is some of the challenges that the open source community is reporting around healthware and health and medical. So things like hurdles to getting certified in other countries and getting certified in the US. Things like the legal risks with entering the health and medical space. And so the width of these columns corresponds to the frequency in which those ideas were represented in our data. And on my left side is some of the quote unquote good futures, things that we're hoping to accomplish with our project. So to help it build trust and confidence and visibility for people developing open healthware. And we can kind of run through the gamut and we'll share this presentation with you. But generally, we're trying to help people address those 4 themes of documentation, globality, marketing, and reproducibility. And so something else I'm doing in parallel with that is, again, trying to analyze some of the workshop data we have in something like a Likert community study. So we talked about those 4 core themes that were identified in our notes that we took of participant information. And so from those, I was able to identify some sub-themes like clarity and transparency of documentation, validation and trust around reproducibility, et cetera, et cetera. I'm going to skip through some things here, but essentially wanting to score the inputs from participants in terms of themes they clearly mentioned, all the way to themes that were absent or contradicted. And so I'll give an example. Like for the documentation topic, I went through and found, the higher scores and the larger width corresponds to higher prioritization or higher scores. And so some of the things we saw is a huge constraint for documentation in the healthcare community is regulatory documentation. Obtaining that is expensive. Producing that is questionable at best. But stakeholders really desire that in addition to things like validation documents and wanting clarity and transparency around those things. And so with these data, I'm developing these so-called narratives. So the idea that our stakeholders want validation and regulatory documentation to reach the goal of interoperability. But some of the constraints are liability around producing documentation. And so I did this for the 4 themes of documentation, globality, marketing, and reproducibility. And this is still an ongoing process. So this is just the online and in-person workshops we've had so far, and just viewing them through those themes and sub-themes. But I'm also cross-categorizing them. So, some people going through the workshop day, they might have felt like, hey, I said something in the first room, and in the second room, I said something different, contradictory, and I'm leaving. I don't even know if we said anything at the end of the day. But in reality, the way that those conversations evolved and the way that people interacted with one another and shared ideas and came to consensus in these local dynamic pockets is really interesting and valuable. And that's what I'm trying to study as I go forward. So just to again mention and kind of build on what Alicia was saying is that we are eager to get certifications from people to try and build this community in a centralized, standardized, open way. And we're grateful to people who are looking to get certified. And, we have those over 3,000 certified devices represented all over the world. So I'll hand it back. Thank you.
So with that, we had a few other key points that we saw, and just really, I think the most important thing that we want to really highlight here is that 1, transparency is key, and people are looking for alternatives, right? Alicia started off by saying how generics are a thing that's very useful for us, how it's important that people can get the insulin and things that they need. And so people want alternatives or parallel systems to the current ecosystems that we have in the healthcare units. But people also want to be positively recognized for their work. And so that's a key thing that we want to make sure that we do, but knowing that it's also a double-edged sword. While people want to be positively recognized, they also don't want to be recognized for hurting someone, because people ultimately don't get in the open to do harm, right? But how do we make sure that we keep things safe, have some form of quality control, whether that's with us or not, while also positively recognizing people for their work. And then last but not least, being aware of misnomers, right? Sometimes people will talk about documentation, but they mean something else. Sometimes people are talking about safety, but they want trust. And so Keeping these things in mind, some future directions are fairly simple. We want to continue to poll you both here and abroad about gathering data. We want to continue to take this information. So please take the survey, which you will hear us talk about the entire weekend. And then lastly, but not least, we also hope to create some content, create educational materials to make people more aware of the things that are available to them, both from a resource standpoint and more. And with that, we thank you for your time. And so now, to keep in the theme of OSHWA, I want to present to everyone Joey Castillo. So Joey also has a role at OSHWA as an open healthware engineer replicating healthware devices. Joey is a software and hardware engineer and is the technologist in residence here at Cornell Tech in New York City. He's also the founder of Oddly Specific Objects, an electronic practice that publishes open hardware designs and manufactures open hardware products in the wearable and hobbyist space. So with that, Joey, come take it away.
Thanks so much, Eve. Let me get my slides up here. All right, cool. So as Eve mentioned, my name is Joey Castillo. Clicker, obviously. And coming up with a name for this talk was hard, but I ended up on why do we do what we do, which I promise is not going to be mopey and existential, but is actually going to be filled with action items that we can think about. So as mentioned, I am the technologist in residence here at Cornell Tech, as well as the open healthware engineer here at OSHWA. And in that role, we've been talking a lot about replicating open hardware devices and stuff like that. So I was initially going to give a talk about just like, hey, welcome to Cornell Tech. Here's cool stuff we do in our lab. But this question of why we do what we do has kind of permeated a lot of my discussions here at the OSHWA grant. It's also a question that I think a lot about in my own practice, because in addition to being technologist in residence here at Cornell Tech and healthware engineer at OSHWA, I also make and sell my own open hardware objects, like a sensor watch, this board swap for a old Casio wristwatch that I'm wearing on my wrist, that turns it into a kind of a wearable sensing platform, and the open book, my kind of long-standing attempt to build an open source ebook reader. So I kind of broke the talk into two sections. First, open hardware before bringing it back to open healthware. And I thought this might be important because a lot of folks in this room come from different lenses, different places, and not everyone might know exactly what we mean by open hardware. So yeah, as Eve kind of alluded to, the existing OSHWA certification asks you to share open source design files, software, if there is any, and documentation. And that's kind of like the gist of what's required to get an OSHWA certification right now. These items come from the, and in making the open book, this is an open hardware object. That means that I'm sharing my schematic diagrams, I am sharing my board design files. All of these things are open source and you can download them and look at them and do what you want with them. But why? Why do I do that? Why do we do this open hardware thing? So I put up the open hardware definition, which is kind of long here, or at least is the first clause of it. Open hardware is hardware whose design is publicly available, study, modify, distribute, make, sell. It mentions preferred formats, but there's this sentence at the end that I feel like gets to a lot of people's why for doing open source hardware, giving people the freedom to control the technology in their lives. And this is a big why, I think, and I think a lot of folks come to it from here. But I kind of want to go back to the first sentence here because there are some whys embedded in these sort of action words right here. We want to make hardware that people can study, hardware that people can modify, distribute, make, and sell. And each of these are their own sort of whys that can kind of inform the way that we make open hardware. I have this quote from Bunny Huang that I absolutely adore. It's from an old blog post on liberating a smartwatch from the cloud services it was attached to. Bunny writes, the point of open source is not to ritualistically compile our stuff from scratch. It's the awareness that technology is not magic, that there's a trail of breadcrumbs that any of us could follow to liberate our digital lives. So I read this and I think to myself, cool, what are those breadcrumbs? And more importantly, can those breadcrumbs be different depending on the why we bring to our work? So yeah, If open source hardware is hardware whose design is made publicly available so that people can study, modify, distribute, make, and sell it, how do those action verbs change the kind of documentation that I share? And crucially for us, with the bigger set of whys motivating people to make open healthware, are there other design documents and artifacts that we need to consider that may not be part of the original open hardware definition? So again, I said this first half is open hardware, then we're going to bring it back to healthware. I use open hardware as this lens because the open book is a device that I've designed a whole bunch of times with several different whys. And I figured before we get into the healthware whys, we can talk about the hardware whys. So when I was first designing it, I kind of had this habit of covering every square inch of my silk screen with explanatory text, giving me the nickname, the Dr. Bronner's of PCB design. But I did like the idea that in addition to publishing the files online, the silk screen kind of was a front and center piece of documentation that folks could like see when they got the object in hand. I can't get rid of that thing, whatever. So I used the silk screen when I was thinking that I was making a device for people to study to explain how the device worked. So you could read about how the power supply worked or how the language data was stored in a flash chip. Like explaining how the thing worked was a way to make open hardware that someone could study. But later on, when I wanted to ship it out as kits that people could assemble themselves, I used my silk screen as step-by-step instructions. The idea that this is optimized for making. You go follow step 1, you follow step 2, you follow all the steps, you end up with a working open hardware gadget. These both fit the definition of open source hardware, but by putting different things front and center, I had a different why in mind. Hardware you can modify. When I wanted people to start hacking on the firmware, I put pin definitions and notes about how to develop software for it on the board itself. The idea being, I am inviting you to hack this thing rather than just make this thing. Hardware you can distribute. At some point, I got sick and tired of mailing out kits. So I was like, just fine, make it on your own. Like, have a factory do it. So I shared the Gerber files you would need to send to a place like JLC PCB and a BOM with the actual part numbers from LCSC you would need to send it. So you could just take these 3 files, send it to a factory in China, and get 5 open books in a week. And again, the why of distributed manufacturing is different from the why of like understanding it if it's a device that I want to sell. I'm basically inviting you to eat my lunch here. And for me, that why made sense. And as far as hardware you can sell, I've even gone so far as to give talks where I open up like the internals of my business and talk about my cost of goods sold, my margins, and like the prices that like why the price I charge you is not the price that I pay for it. I can see this being very uncomfortable for some people in open hardware, but for me, for my practice, this is what I want to do. This is my why. So yeah, I will be the first to admit, some of this might not be you. And lots of folks come to open source hardware with different whys in mind. And I'm going to repeat, the OSHWA certification doesn't require many of the things that I just showed. It merely asks for open source design files, software, if any, and documentation. So yeah, back to the open healthware piece. With a bigger set of whys motivating our reasons for making open healthware, are there other design documents and artifacts that we need to think about? Which brings us to section 2, open healthware. So yeah, we've been examining, or at least in the OSHWA grant, I was brought on to examine open hardware through the lens of replicability. Can we make this in our lab, right? So yeah, open source design files obviously include our schematics and Gerbers and things we need to fabricate the device, 3D printing, STL files, what have you. But as Eve mentioned, test and calibration procedures could also be crucial here because we made it. How do we know it does what we wanted it to do? How do we know it works? Does design files include assembly instructions, or is it something that should be obvious? Do we need a bill of materials? I think this was a question that came up in pretty much every meeting that we had. Sometimes the bill of materials can be the secret sauce to making something work. But if you're trying to be open, do you need to include that? Also, a BOM sometimes includes many parts. Sometimes one part's out of stock. If the part's unavailable, should we explain how to select an alternate part? Or if a part isn't readily available, do we need to suggest a qualified vendor? Because vendors can also be secret sauce, right? A good example of this is in the course of the OSHWA replicability studies, 3 of my master students actually replicated PicoRic, a open source ultrasound sensing device, in order to explore new modalities around ultrasound sensing for bone density. So this is an open hardware device that they basically downloaded the bombs, downloaded the Gerbers, fabricated it, assembled it in our lab in Cornell Tech, and yeah, started exploring ultrasound sensing using this open hardware design. So that is replicability right there, right? Having said that, distributed manufacturing, while kind of having this similar like rhyme with replicability, might have different constraints, right? Can people make it on their own? This could be distributed DIY manufacturing or distributed mass production. This was something that came up in a meeting last week with Victoria from Open Source Medical Supplies. There's these feeding tube connectors that seem to be falling out constantly. And people who like have to care for a loved one and deal with these feeding tubes make 3D printed retainers for them that like solve their problem and then share these STL files in Facebook groups. This is open source hardware, like sharing problems in the community and finding solutions, right? But the glia tourniquet's also a good example of optimizing for distributed manufacturing, but in this case, focusing on mass production in distributed supply chain, disrupted supply chains when you're in a war zone and you need to like 3D print on your own. So yeah, these might have different, like if you're trying to replicate at scale for real world impact, what would you share more about, right? Would you share more about costs? Field Ready actually has in their database production costs associated with many of their open source designs, which kind of makes sense, right? If you're gonna try to like take a device and deploy it in the field, you might wanna know what you're getting into in terms of expected costs. Maybe it's not actually cost effective or you need to optimize the design. This might be something that's uncomfortable to share if you're selling a device, but if your why includes getting people to make it on their own, this might be important. Risk analysis is another good example. Field Ready also shares risk analysis of all of their things, where someone's actually like gone through the design and evaluated the risks, both to the people making the device, i.e. you could burn yourself on the 3D printer, and people using the device where, oh, the hazard is the device could become unclamped, right? So this kind of risk analysis, again, is not currently required by the open source hardware certification. But as we talk about why are we putting open healthware out there, these might be the kinds of documents that we want to share. Do we need documentation of crucial design decisions? This came up in a conversation with the glia folks, where the tourniquet's print orientation actually has a huge impact on its physical strength, which you need in a tourniquet. So if you just lob the STL files over the fence and expect people to print them, that might not actually work in the field unless you also document the fact that you need to print these STL files with a certain orientation. Otherwise, your thing's not going to work. So yeah, in the case of deployment in the field, I'm wondering how do the deliverables look different if your why includes a lot more people that aren't open hardware people in the lab, but are people out there doing the work? A couple of other lenses, and these are not by any means exhaustive. Open hardware for repairability. It occurs to me that a lot of folks get into open hardware because they want to fix things and mend things and keep things in service for longer. So yeah, maybe you can't make the entire thing yourself, but can you repair it? So yeah, obviously design files from the replicability frame might still apply here, but do you need a disassembly guide possibly for this kind of thing? Revalidation procedures. After you've done a repair, how do you know that it's working the way it's supposed to or the way it worked before? Troubleshooting guides. And here, there's actually not quite open source hardware, but iFixit has a really good kind of framework for this, where their guides describe how to troubleshoot and debug and disassemble and reassemble devices. This is for a Cardinal Health ventilator unit, which is not an open source hardware device, but by documenting these faults and giving people the power to diagnose them themselves, yeah, we're opening up something about the hardware. And if you were making an open hardware device like this, what kinds of guidance might you include if you're trying to help people to repair it, even if they can't build it from scratch? So yeah, this why might lead to less documentation in some places and more documentation in others. But the point I'm trying to get at with this talk is just thinking through those whys before, before putting your stuff forward. And yes, we do still hope that you fulfill the open hardware definition of open source design files, documentation, and software. But again, some of this may not be you. There are lots of folks in this room with lots of different whys for what they're doing. And the point in this talk was to just, again, asking this question, why do we do what we do? Not as a mopey existential question, but as an action verb question of, with our given why, what information do we put forward? So yeah, it's worth thinking about and articulating the reasons you want to be open. And it is fine if those reasons aren't the same as everyone else here, right? But I think the reason this is important to me is beyond the baseline of just open design files, we do expect the open healthware ecosystem to develop new norms and practices around what ought to be shared to accomplish the goals we're all setting out to achieve. And that's, I think, what this conference and these meetings are all about, figuring out those norms as a community. So that is the talk that I have for y'all. And yeah, thank you.
Hi all, my name is Heron. I'm the Healthware Community Coordinator with OSHWA. I'll be introducing some of our speakers today and tomorrow. Our next speaker is Alex Hornstein. For the past 20 years, Alex has worked as an independent inventor, creating new ideas and getting them out into the world. When he's not in the lab or behind a lens, you can find him on the tops of mountains or the bottom of the ocean. I had the pleasure of meeting Alex at our New York workshop earlier this year, and I'm excited to announce his talk, sorry. His talk is called Take a Deep Breath, a story of ventilator alchemy under pressure. Welcome, Alex.
Thank you. All right, folks, how's everyone doing? Can you hear me? Yeah. All right. Whew. Well, I just flew in from Manila last night, and boy, are my arms tired. All right, so we're going to talk about ventilators, and this, of course, is something that comes during COVID. This is a complex topic, and so I'm going to try to split it to about half human stuff and half lungs, and everything in between. So before we get into it, I want to just give a note of introduction for myself and the sort of work that I do. So I find that the projects I work on tend to shift decade by decade by decade. And for about 10 years, I spent my 20s building rural electrification devices, working at the edge of the grid and putting solar systems in where there was no electricity. And this is a typical portrait of what this work looks like. A lot of climbing at the rafters and putting stuff into corrugated steel roofs and what have you. I really liked this work for two particular reasons. So one is that this is kind of a classical application of technology where it makes a difference in people's lives. And it's a combination of, the work that I trained and studied and practiced to do in electrical engineering and computer science. And at the same time, it's an exercise in fighting against entropy, where there's a million reasons why this intervention you're trying to do shouldn't work. And it's kind of a battle of will and of connecting and bringing people together to try to push against entropy, to make this thing that doesn't really want to exist. A house that is way up on top of a mountain or across several miles of ocean doesn't want to be connected to a perpetual source of electricity. And there's lots of things like typhoons and saltwater and landslides that tries to keep that from happening. So it's this constant battle against things that are trying to keep your idea from working. And of course, I could stay here and go work for General Electric and build, power line transformers, and there's no huge battle against entropy. Someone has taken care of that. But I liked this idea where no one has taken care of that. You can choose to make this intervention or not. And I like this one because you can see the results. And also, it's not boring. I actually really like this. In fact, a lot of the issues that come up are human obstacles to progress. This was one example of electrification we did in a village on top of Mount Makiling in the Philippines. And this village was not electrified because the mayor at the base of the mountain wanted the people in the top of the mountain to be out, and so had actually removed electrification from this village. And when word got out that we were going to bring panels up, they put a blockade on the road going up. So it was a roadblock, and they were looking through, making sure that no one was bringing panels up the mountain. And village had a couple horses, and they're like, there is a path on the back of the mountain, and there's no blockade on the back of the mountain. And so this led to this kind of whole complex path of, getting this huge wobbly, literally packed solar panels in a box that was for refrigerators so that it wouldn't attract attention. They came shipped in from China in a big refrigerator box, ended up at the base of the mountain, loaded them into horses. Loaded them into horses with some images, which unfortunately we don't see because they're spectacular, including schlepping these panels up. There's my wife, Hannah, who at the time was 4 months pregnant, ended up going on top of the horse with the panels up on top. And this is kind of like a characteristic installation, is it's full of a complex mix of humans and technology. And the end result is you apply technology, you do an intervention, people end up happy with it. I don't do this anymore. Around shortly after that particular installation, we learned we were going to have a baby. And there's an interesting thing, which is, like this sort of work, you end up going from place to place to place. I think I was living in 3 different countries at once and kind of right on the raggedy edge of existence. And everyone becomes a little bit more conservative when you're going to have a kid. And I started a holographic display company, which is actually based here in Brooklyn, still around. And this is the kid, by the way. She's over there now. Her name is Lumen, and has been the center of a lot of light projects throughout her life, and hopefully will continue. So the reason I bring up this kind of backstory is we had started this company, and this company, Looking Glass, it had its headquarters here in Brooklyn. We had offices in Hong Kong and Shenzhen, and I lived in Pawtucket, Rhode Island. So we really had presence in the big 4 cities around the world. And every day I would get on the phone and I would talk to people in each of these locations. And be bouncing back and forth. I'm in New York every week. I'm in Hong Kong every couple months. And I'm constantly involved in the making and production of things. Around, I don't know, say November, December 2020, there started to be a large yikes in these conversations where something was clearly going wrong. And, I'm hearing it from the folks that, like, I'm talking to in Shenzhen, is people weren't going out. Restaurants were closed. Like, something was an unusual thing that none of us had seen in our lives. And then we started seeing news like this. Ventilators, there's not enough ventilators. And, so this, increases the yikes level. And it kind of raises this question, like I'm reading this and kind of like, well, this is just hype. Like someone has a plan, like at the base of this, like there's a plan for what to do. Like as long as it might not be good, but someone has a plan. And I don't know if any of y'all New Yorkers would tune into Cuomo's like nightly talks at this time, but I remember very vividly this talk where Cuomo said, for out events, we're going to recruit a lot of healthy people to squeeze these bag valve masks. And that's what our hospitals are going to look like. And I was like, oh, that's not a plan. That's really, really bad. And, look, the reason I talk about this design for work in low resource environments, the reason I start that way is because New York is not a low resource environment. It might be the highest resource environment on the planet, except in a pandemic. In a pandemic, literally everywhere is a low resource environment. There is no such thing as high resources in the face of a pandemic. And kind of watching these ideas falling apart. Like, gosh, like this is what we got. We should have something better than this. So moving on, I started, this is probably around January, February 2020. I thought that the right thing to do is to lock myself in a room for like 2 days until I came up with a plan. And I should mention, I don't do medical device design. I don't know anything about medicine. And there's no particular reason why I thought I should make a plan, except that the absence of a plan bothered me. And I kept just seeing everywhere I looked the absence of a plan. And I'm like, I don't know where it's going to come from. It's kind of like the Kitty Genovese thing. Like everyone thinks someone else called the cops. Like just stand up and call the cops. You know, make a plan, whatever it is. Like if there's a problem, like go and do a thing. And if you're redundant, that's also okay. So I started making kind of like this to-do list for how the plan's going to work. So one is figure out how to make about 500,000 ventilators appear. Part two is get into the room where people are like deciding how to move stuff around for a pandemic. And part three is convince everyone in the room that this is a good idea. And then, you know, scale it, like keep making it go until this is solved your problem. This should look like a naive to-do list. If it's not, like, I appreciate your optimism. And something I kind of noticed during a crisis is that this is kind of like new observations for how people work. One was like my state, live in Rhode Island, my state's Department of Health put up this form that's like submit an idea to the Department of Health. And it was just a Google form. And you could type stuff in and never hear anything back. And that was weird. In fact, there was a lot of things that was weird. A lot of these kind of like normal interfaces with large institutions stopped working. Like people stopped responding. They would get overwhelmed or they would get clogged up because business as usual wasn't usual. But this other side of it was neat, which is that you could still call your friends and you could still call people you knew or people you got introduced to, and they would pick up the phone, even if, let's say, a Department of Health would not. Even if, like, and you know, whatever these typical ways that you would approach a larger group, those might not work. But if you knew a person who worked there, that was a way to get in. So you had to kind of learn wayfinding in a whole new way to get stuff out. You had to learn how to navigate along social lines. A couple other things on working in a crisis. So a big one for me was, you know, you could make like 5 devices, but this is a project that was applying to millions and millions of people. Even though I didn't know how to make millions and millions of ventilators, trying to make something that could be deployed at the scale of the problem was key in designing a good intervention here. And then a couple little addendums. So first of all, like the heartwarming thing about COVID, everybody wanted to help. And including like at every level and strata I've ever seen of society, except possibly the leadership. But despite that, like extraordinary things could happen in extraordinarily short amounts of time in a way I've never seen replicated before. Like one example was a weekend project where New York City was trying to figure out how to get like several 100,000 of these oxygen adapters for CPAPs. And we knew we could 3D print them. We didn't know if the medical grade 3D printing was compatible in a pure oxygen environment. And so I called a friend and I was like, do you know, just out of curiosity, I don't know, like how we could do a very detailed chemical test on off-gassing of a device that might cost millions of dollars to see how this works. And my friend's like, yeah, I know a guy. And so I like wrote on a napkin, like this set of tests of like, okay, we want to 3D print some of these things with this finishing process and with this one. And within 24 hours, we had this delightful mass spec results back. It came with a very large bold-faced thing saying do not distribute confidential, and so I confidentially did not distribute it. And as it turns out, a print farm very quickly, like within a couple days, started making these devices. We found there was a practice making them not off gas, and all of a sudden this could very quickly roll out. Again, I'm not normally in the business of writing mass spec tests, but people were willing to ask, as long as you could fill in the gaps, like glue together the things that people could easily do with what they have in front of them. So I learned to kind of just ask for a lot of stuff. And I asked for everything from human help to devices to money and everything in between. And then the final thing for me was don't try to make money. Like my goal here was get stuff out the door quickly, like get vents onto lungs. And if I want to do that quick, because this was on a 3 to 4 month time scale that things had to happen, I didn't want to spend time worrying about making money or protecting stuff or wrapping it in layers of confidentiality. The things you would normally do is kind of good business. I wanted to pass through that. And then one final thing was, because of course I don't know anything about medicine, I wanted to convince myself that I was doing some good work. So to try to inform myself about medicine, I reached out along social lines and I said, who can connect me to a pulmonologist who can talk for roughly 8 hours a day for a week? And delightfully, I got connected to a man named Dr. Viral. That is one of my favorite connections of the pandemic. Dr. Viral is a pulmonologist who had just had a 2-week-old baby at this time and was at home and was really happy to have something to do that was relevant to clinical study. He was a sleep medicine pulmonologist, which is different than like critical care pulmonology. And I just began to pepper Dr. Viral with questions and got like a week of intensive instruction in pulmonology. One of the key questions at this time, I also reached out on social lines and ended up in the room that was figuring out how to put ventilators into hospitals. And this room every day would look at things like this, which was a week-by-week forecast distributed by the CDC of when you would run out of ventilators in each state. And this was a really unpleasant way to start your morning. All the meetings were like first thing in the morning. And you wake up and you're like, oh my God, it's all scary. And so this was really like, okay, like we're working on a tight timeline here. And I want to find something that can roll out. Around the same time, for those of you who aren't into vents and pulmonology, just to kind of run through, lots of different types of ventilators. It's a whole spectrum. And we decided early on in the pandemic, when I say we, I mean the WHO, to not use the red flavors of ventilator, which actually meant we lost our most common type of hospital ventilation. And this made everything a lot more complicated. The concern was that we were going to spray viral particles in the air and get our doctors sick. That's a very valid concern. On the other hand, it made it really hard to treat patients. And WHO thinks on both sides of this. I appreciate their concern. This led to people trying to intubate patients very quickly, which had its own sequelae and difficulties. But so, around like March 2020, we see that the US wants about 500,000 ventilators within 3 to 6 months. And having worked in production, we have companies that make ventilators. They can't do it. They have supply lines set up to make vents. They can't do that. We kind of know if they are not going to do it, nobody else can do it. So what can we do with what's already out there? Around this time, like mid-March, Johnny Lee, who's a kind of presence in the open source community, put up a really interesting blog post, taking apart his own CPAP and thinking about what's in it. At a quick show of hands, who here uses a CPAP? CPAPs, woo! So these are sleep apnea machines. They blow a hurricane of air into your mouth while you sleep, and this helps open your airways. It's also the most common respiratory device that's out there. In the last decade, we've put out about 10 million of them across America. And it turns out, I learned from this teardown, that all the blowers in every CPAP and ventilator are the same thing. There's only two manufacturers of them in the world. This was the key bottleneck. This is why we couldn't make more of them. Another thing is CPAPs get replaced by insurance every 4 years. So there's and they have a lifetime of 7 years at a minimum using 8 hours a day. So there's a bunch of CPAPs with useful life sitting on a shelf. In fact, more than 6 times what America needs was just sitting on shelves. So I kind of started figuring out, without a full plan, let's collect them. Now, what's the difference between like a life support vent and a CPAP? I don't know, looking at them. The blower is the same. The pressure sensing is the same. It's got a microcontroller. It's got some hose connectors. It's kind of the same thing. And I actually started going through these and saying, well, what is the difference between a home use sleep apnea machine and a life support vent? And there isn't a technical difference, with one key exception, which is an alarm if it gets disconnected, is the difference between a life support vent and a home use one. So real quick, if you go to business school and someone's like, hey, you're going to run a company and you're going to make some products, they're going to tell you you should sell 3 products in a product line: a beginner, an intermediate, and a pro, and you should charge more for each one. They're also going to tell you it's a big pain in the butt to make 3 different things, so you make one thing and you cripple it in firmware. So the nice term for this is market segmentation. But what I kind of was starting to guess was you could write a firmware that would let this basic thing work like a fancy thing. We'll skip through this. So this question was on my mind, and I reached out on social lines to the guy who is the largest distributor of CPAPs in the world. His name is Johnny. And I started asking for every model of CPAP that he could send me. And think about firmware and reverse engineering firmware. I got connected to another guy who is a particularly capable firmware reverse engineer. And I started firing every model of CPAP over to him in Amsterdam and saying, can you write a program that, instead of just blowing a constant stream of air, starts to flip it off and on? This is the basics between we call a continuous positive airway pressure and a bi-level positive airway pressure, which mimics breaths. And within 24 hours, he came back. He said, well, I could, but I don't have to because it's already on there. So people, of course, had written 3 different firmwares, each of these device manufacturers, and put all 3 through FDA on each device, so that you could just flip one bit that said, I'm a BiPAP, I'm a BiPAP ST, I'm a CPAP. And depending on whatever you said, even though it wasn't in the right box, it would behave like the different flavor of device. At this point, I got really excited. I started running around like a Muppet, like with my arms like waving around, and trying to figure out what this meant. This is an open source project. It's called AirBrake. You can reflash your own ones. They work great. And it just opens up these other levels, kind of like Magic Lantern, for any of you who are familiar with camera hacking. So yeah, I mean, even though these are not consumer devices, they follow the same capitalism logic that everything else does. And then this other interesting thing happens. As soon as you say the word firmware out loud in medicine, people's eyes do that thing that sharks' eyes do when they're about to attack you, where like the nictitating membrane comes in and like just turns milky white, and you're like, I'm about to get bit. Like something happened. I don't know what it is, but something bad happened. And this question of how do you certify a device that has the same firmware that the manufacturer put on, but you just switch which one is running, is a thorny medical question. It is a difficult one, even in the face where this is a clear positive. That is a difficult question. So this one I actually left. This particular insight, I said, this is an open source project. I collected a bunch of CPAPs. And when it came to getting them into hospitals, I said, I'm going to get the unmodified ones in because that is faster. This will add 6 months of questionable timeline. And right now I want to get a lot of devices into hospitals. So running through these, I said, all right, I'm a little bit sore about that. I think it's annoying. I wish you could get more capable devices in. I found this frustrating, but what are you going to do? We quickly started throwing up this little box, which my friend Liam made, and just like padlocked to the outside of my building in Pawtucket, Rhode Island. And then we somehow convinced the state to broadcast they drop off your CPAPs thing. Shortly after that, the state got shamed into giving us a truck and letting us donate them in every fire station in the state. And then they got shamed a little more into giving me the University of Rhode Island and 150 grad students to make a CPAP reprocessing facility that respiratory techs would teach people how to collect and refurbish CPAPs. We started getting these trucks that would come in. People started bringing in huge amounts of these devices. We started collecting them like crazy. At this point, we had like, wads of devices on a table, but it didn't look like a thing. So this is where the reason we live in Rhode Island, and I went to RISD, all of our friends are artists. And artists, what good are a bunch of artists in a pandemic? Well, this wasn't a technology problem. This was an art problem, or as engineers like to call art, documentation problem. And this was the documentation problem. This was my Sharpie drawing. And if I showed this to a doctor, they would like take a sip of coffee and just. So good news is you can give this to a good artist. And all of a sudden it looks like a medical device, because it is a medical device. You just have to make it look the part, okay? And this is an interesting thing. Another common thing with a home use device is you gotta be able to fiddle with the settings. Every pulmonologist says, every res tech has to do this. And on a home device, they are hidden because there is some amount of distrust for users to adjust their own settings. So each one has a secret cheat code, like AA, BA, up, down, start, where if you hold down stuff for a certain number of seconds, you get into the secret menu and you can adjust it. So printing and laminating ID cards for every model of CPAP in existence and putting them into their boxes became a key part of getting these usable in hospitals. So how do they get into hospitals? Well, you kind of got to make them into a product, because pandemic or not, we buy into a product, a thing with a predictable box and an instruction guide. And so we put in this stuff, including this thing, which is a helmet that you put over your head, which lets you filter the air coming out from getting into your healthcare workers' lungs. We figured out how to get all this stuff. We got a lot of it. And we started putting it into boxes. Around this time, I was obsessed with this one question of, this is about to get used. Like, all these are going out the door. I could have just let them go out the door and let doctors deal with this. And I'm not super smart. This paper was bothering me, which said, these were results of invasive ventilation in Wuhan. And there was a similar story in Lombardy and a similar story in New York. Invasive ventilation in New York had about a 12% survival rate. This was a last resort. And it did not have it was a huge use of resources. You have to do this in an ICU. It's a life support setting. And it wasn't really paying off necessarily. You could throw all your resources at it, but it wasn't a good outcome for most patients. And again, I mentioned this thing of, in a pandemic, every place is a low resource setting. And even if you can get more stuff, you don't have more ICU doctors, you don't have more ICU nurses, you don't have people who are in this constantly, who are super trained. And so just having ventilators doesn't make everything turn out okay. It's a last resort, it's important to have it, but it's not the thing you want to use on everybody. And we saw this, we learned this unfortunately, and each country relearned this lesson for themselves. And it raised a second question. So this is around May 2020. This didn't work great in New York. What's it going to look like everywhere else? How can you make this useful when your healthcare system is under strain? And this led to kind of the final iteration of this, which we called circumvent. Get it? Dr. Fred Allen was very proud of that title. So this was an idea of how do you use these low-end ventilators for people who are mildly or moderately ill rather than severely ill to avoid them getting worse. If you had a limitless amount of these devices, which you can, how do you deploy them in a sensible way? And we, at some point around this time, we're asking everybody, can we get like $7,000 to send like a couple pallets to this place? Like, wherever it was, we said, we have all these devices, they're free, we just need shipping. And at some point we approached the CDC Foundation, who said, no, we don't fund untested interventions. We said, but this is a device that's already throughout the day, let's go. And they said, no one has tested this in a global respiratory pandemic. And I was like, and they said, well, we do fund studies. We said, oh, a good study would be if you had a lot of ventilators, would it help? And so this began our largest intervention, which was running the ventilation program for the entire country of Nigeria and working with every COVID ventilation center in the country, training about 300 respiratory staff. This is our best documented and studied intervention. We worked in 26 countries, but this is when we got data from and built the infrastructure to hear back. And there's a whole bunch of stuff I'm going to skip through real quick. But point is this. Look, we have data. Sometimes I look at it and I think about, did this help? Was this a worthwhile thing? And the answer is yeah. A lot of people were put on our vents that got better on our vents. And I know I can't say what would happen if the vent wasn't there because this wasn't a double-blind study. But I can say it probably wouldn't have been there if we hadn't sent stuff. This is true in a lot of different healthcare systems. So I'm very glad that we had the opportunity to put stuff out. This is the CPAP shed at this time. Around 2022, we turned into the chicken feed shed in the back of our house. This is Lumen digging some kind of hole. And I'm very happy to kind of put this project to rest. This was a single purpose organization that was designed during the crisis part of COVID. Don't really need to be doing vents anymore. This is a fine thing to have done. I'm very happy we did it. I'm very happy to put it to rest. And for the huge number, it's about 175 people who helped organize and work this. I'm extremely thankful, but above all else to those two over there. So thanks for your time.
Thanks, Alex. We're going to take a short break and be back in the room at 11:05. Feel free to take your things with you, to get a snack, go to the bathroom, but we'll reconvene at 11:05. Hi, all. We're going to get started. If you want to find your seats, wrap up your conversations, even though I know they're good. All right, we're going to go ahead and get started. I'm going to introduce the next speaker. Teresa Buxo is a biomedical engineer and creator of Care Again, a collaborative platform focused on making medical technology more accessible by sharing open source projects and fostering a global community. Please welcome Teresa and her virtual talk, Care Again, a community-driven prototype platform to make medical technology more accessible.
Hello everyone, and thanks for this opportunity of presenting in the Open Healthware Summit. I hope you are enjoying this meeting, this summit. And well, I'm Teresa Buxo, and today I'm going to present about Care Again, which is a project I started about a year ago, and is a community-driven platform to democratize access to medical technology. And in this presentation, I'm going to show a little bit of the journey that led me start this project. So let's start with a little bit of background. I am a biomedical engineer. I studied in the University of Barcelona and then in Trinity College. And since then, I have some experience in both in academia and also in the startup industry in medtech. But also I did some volunteering experiences, one in Cambodia and one in Guatemala, that opened my eyes of how, like, the potential of the open source world and also the challenges in the global healthcare systems. So I'm going to explain them a little bit more in detail. Cambodia was the first contact with open source hardware that they had. And one thing that you realize once you arrive in Cambodia is the problem that they have with the plastic waste. There's plastic waste everywhere. So when I was there, I was like, what can we do for this? So I started to search on internet, and then I found this community called Precious Plastic. For those who are not familiarized with that, is a global community that they want to tackle the problem of plastic waste by recycling locally, so building machines and recycling locally. And they have this community map where you can connect with other precious plastic workshops. So I contacted one of them that he was in Cambodia at the time, and he was doing some sunglasses with the plastic waste. What I found very interesting from this, it was like I arrived to Cambodia and I didn't know anyone, but I still could contact someone that was doing something that I wanted to do as well. And that's like, that shows the potential of just open source hardware. At the end, the project didn't work out because we were very far, even in Cambodia, we were very distant. But it was like very interesting to see. And the other project that I saw, it was the Mekong wheelchairs. So a little bit of context. In Cambodia, there's still some landmines, and also there's polio and post-polio disease, which both of them limits the mobility because like both the amputees and also the polio patients, they cannot walk as they would like to. So then there was this Spanish bishop that he was researching, and it was like there should be a way to improve this their mobility and also help them to go around. So the association that he was directing, Karuna Vatavan, and also another association which is called Motivation, which is an organization that they build and design wheelchairs. They joined together and then they designed this Mekong wheelchair that was able to be produced locally. So then they started to produce it locally in the Jesuit Refugee Center, and then they could just give those wheelchairs to everyone that needs it. And here I am with one of the patients. So it was very, very powerful, the power of just producing locally, very close to the need, and it was sustained in time as well. And the other experience that I had, it was in Guatemala. And here there was another issue. It was the problem of abandoned equipment. So there's loads of donated equipment that they cannot use because the maintenance like is they don't know how to maintain it, they don't know how to use it, or there's still like some pieces missing, or the devices they arrive and it's not what they were expecting. So there's a lot of abandoned equipment. So I was collaborating with this association, which is the Engineering World Health, and what they were doing was training some students to do small fixes and also to help to train also the staff in the hospitals to maintain those medical devices. So the fixes were quite easy, like it wasn't like big fixes, but that allows to have the equipment working again. And this just gave me a picture of it is not just the access to medical technology, but also the training and maintenance to make them usable in countries with low and middle income. So with these experiences, I started to search a little bit like how can we do this medical technology more accessible and more usable in those places where it's sent or where it's going to be used. And then I came to this World Health Organization report, which states the problem, which is more than 50% of the world population lacks full access to essential health service, which is a lot. And not only that, but there's approximately the 17% of world's population that was pushed into poverty by paying the health expenses that they had. And if we see like the solution that we were given, it was like donating medical devices, but we see that there's only the 10 to 30% of those donated medical devices that are going to be operational in low-income recipient countries. So I was searching a little bit like, what can we do, or the state of the art right now? And then I saw like the traditional medtech ecosystem, like most of you are already aware of it, but in general, medtech, like the medical devices, are very high costs, and this limits the access in many regions, which this creates a healthcare, like a lot of disparities in healthcare, especially in those countries that they cannot access to those high costs. And also most like almost everything of the development of medical devices is in a closed environment, which makes sense because from the idea to the market, it takes a long process, and you have to do some like clinical trials and so on to pass regulations. But at the end, what happens is like it makes the innovation very slow. So I was thinking like there should be other ways to innovate in medtech. So then with Caravan, when I was starting the project, it was like, how can we promote the open source so we can do these projects open source and focus on local production, so the innovation could be faster and easier, and also having this distributed network that we can connect with local hospitals, and we can do like the local production there, like with makers and builders, and this like would do like the accessibility to open to medical devices easier, because it could be more redistributed. And I have to say, it's very encouraging right now, the ecosystem, because there's a growing open source ecosystem. There's loads of different projects, and I'm sure in this summit there's a lot of representation of those open source medical devices projects that are right now growing. And I think this wave of innovation was accelerated with the COVID pandemic, because then we realized how powerful it is to join all the efforts together. But also there's like some initiatives to get the open source medical device certifications. So the some initiatives like OSHWA or Open Healthware, where we have those meetings of what we can do to get an easier path for regulations. And also there's this expanding network of community workshops, all the fab labs and all the makers, that it's just increasing. So then with all this, we started with the proposal of a Caravan platform that bridges this gap of connection between different designers, different makers and hospitals, and also different organizations for redistributing this medical equipment. So right now we launched the prototype, so it's still in very early phases. It's the prototype where we can share open source medical devices designs. So the intention is not to build like a documentation platform, but a platform where you can share and you can link to your own projects, and also having this collaborative ecosystem where you can contact designers or builders or manufacturers or health centers to align the clinical needs with practical solutions. And then there's like, we were thinking about the next phase, and it was more like supporting the local communities. So connecting the different hospitals and that are in the area to just make this redistribution of medical devices as well. And also creating some videos for training, so the local staff in very rural areas, they can just keep up to date with their knowledge. So right now, the current platform allows you to organize your organizations and your projects, and also it allows to connect with the different people of the community, like designers, makers, hospitals, or logistics. It also has like some documentation, still work in progress, so there's needs to increase a little bit in documentation as well, but it allows you to know how to work with the platform, and also if anyone wants to collaborate, it just gives you like the first glance to how to start. And it also allows you to transform the ecosystem by contributing with your open source projects. So I'm going to show you a little bit the demo of the app. So a little bit of the navigation. Just you start and you can log in the platform. and then you can navigate like the home page. You can navigate through the different projects, different organizations, or different users, and it gives you a glance of the most recent ones. And here I put some of as examples, and some organizations as well as examples. And then there's the projects page, where you can just navigate across all the projects. And I put this one, which was a respirator developed during the pandemic. And then you can see like there's like the Git repo or their website, and you can connect there. And also you can download whatever attachments or designs or blueprints that they have. And it allows you to get to different projects. And then there's the community page, where you have this map, interactive map, and you can just see like the different organizations. I put some as an example, and then you can link to each of them, and then you have also one pager, which allows you to go to the different organizations, and also you have the users there. And also there's like a Discord and documentation, as I said. The Discord channel right now is very small, but trying to increase. And also all the documentation, when it explains a little bit more what's Karagan, how, like, for the developers, the guide, how to get started, the homepage, the community page, the projects page, and also if you want to contact, or if you are interested on the license or the code of conduct, you have the information there. That was the profile. So in your profile, you can create your organizations. As I'm creating here an organization like her again as an example. And then, well, let's see. And then you can see there's the organization created, and then you can just edit what you want, and for example, upload the image or put the descriptions. Like right now, I just put it like quickly to give you an example. And you have also the possibility to go to projects and create your projects the same way. I'm not creating right now, but it gives you the opportunity to do it. And later on, we have like a place for feedback, which is you can report feedback or bugs, and it's going to open a Google form to just submit whatever feedback you would like to do. So there are some upcoming features that we were thinking of. Still, we don't know, like we would like also to have like some feedback from the community, but what we would like to was like to grow in this community, and also started doing like maybe some videos of formation. But we are still like don't knowing exactly what we are going to go the path, but just thinking. Also, we would like to have like this distributed network between hospitals, because then if they are not using one medical device, then they can redistribute it to another hospital that is using it, that wants to use it, or something like that. Then we were also thinking of putting like some material kits for the projects, so you can download your material kits and then starting the project yourself. And also with OSHWA and the open Healthware, like all the meetings that we are having, I think like it would be very good to add like some kind of certification with these organizations, like maybe OSHWA, so it gives more credibility to each of the projects. But well, we would like to know your feedback. So yeah, let's transform together the access to medtech. And here you have my contact, so please reach out if you want to collaborate, if you have experience to other projects that they already worked or that they didn't work, and some advice. I'm open to hear any suggestion. So are you in? Thank you very much for for your attention, and hope you finish this summit and enjoy it so much.
Next up is Alessia Romani. Alessia got her PhD in design at Politecnico di Milano and is a postdoctoral researcher at the Free Appropriate Sustainable Technology FAST Lab at Western University. Her research explores the interconnections between designs, materials, 3D printing, and sustainability, bridging design and engineering through open source technologies and materials. She will be joining us virtually for her talk, Addressing Replication Challenges in Distributed Assistive Technology, Insights from the Development of Open Source 3D Printed Crutches.
Hello everyone, I'm Alessia Romani, and today I will speak about one of the works connected with open source assistive technology from FastLab. The title is Addressing Replication Challenges in Distributed Assistive Technology, Insights from the Development of Open Source 3D Printed Crutches. Just quick words about my work. I'm Alessia Romani, and I am a postdoctoral researcher at FastLab, the Free Appropriate Sustainable Technology Research Group in the Faculty of Engineering at Western University. My background is mostly related to product design and engineering design, and I gained some expertise in materials engineering and additive manufacturing during my research path. Before joining FastLab, I studied and worked in Italy at Politecnico di Milano. Here, I worked as a research fellow at the chemical department and conducted my PhD research at the design department, gaining expertise at the intersection between design and material for sustainability. That's why my research interests are mostly connected to the intersection between design and engineering for sustainability, thanks to the use of materials and digital fabrication tools such as 3D printing. I'm currently working at FastLab, the Free Appropriate Sustainable Technology Research Group at Western University at the Faculty of Engineering, led by Dr. Joshua Pierce. Here, I'm working as part of an interdisciplinary team made up of different research and professional figures, such as engineers, designers, scientists, and makers. And we are working together to foster sustainability and enable it thanks to technology. But how are we making it possible? In our case, open source is the way. So we are pushing open and appropriate technologies and trying to make it free and accessible to everyone, fostering sustainability at different levels. We are currently involved in projects mostly connected with two main research streams. The first one is distributed recycling and additive manufacturing, which is also my core topic at FastLab. And the second one is focused on enabling sustainable energy and technologies, such as photovoltaics. In both cases, our focus is to achieve sustainable development goals thanks to accessible technologies, aiming to foster sustainability in real-life context. At FastLab, my activities focus on applying open design principles to physical products and studying sustainable materials for accessible product application. All of this thanks to digital fabrication. You can find us in the Thompson Engineering Building at Western University as part of the Faculty of Engineering, and we are in the main campus in the city of London, Ontario, in Canada. If you want to know more about our work, you can also check our Appropedia page with our projects here. Today, I'm going to focus on a specific project connected to the topics of this conference and open source healthcare. First, I will speak about the replicability of open source assistive technology. I will then focus on a case study that we are working on and connected to distributed open source assistive technology products. I will also share some insights from the ongoing development and validation of this project, followed by some key aspects connected to replicability and future work on the projects as well. Let's start from the replicability of open source assistive technology. But what is replicability in the open hardware context? A possible definition could be the one provided by Omer and colleagues. So replicability is, in this context, the ability of an individual builder to construct a functional hardware version in their respective settings. And this means that the replication should be tailored to users who are prosumers in this case, and local communities as well. And all this process should be supported by open documentation of the designs. Replicability can be achieved thanks to distributed manufacturing because processes such as open source 3D printing allow for more accessible, affordable, and customizable solutions. They can also be available in low resource or humanitarian contexts, for example, having access to a low-cost 3D printer or locally available materials. And all these technologies and materials can support open source local production partners, producing what is needed and only if needed. Replicability is also fostered by open design principles. Project and documentation for open source products should be available to all users. Those products should also be replicable by using accessible equipment and tools available to users. Finally, the replication of these products should be always possible, together with the adaptation or modification according to the specific needs. So the question is mostly if this is enough to ensure real-world adoption. And I would say no, because open source hardware and products should also consider other factors when reaching users and real-world context. For example, easy replicability, quality assessment, or affordable fabrication, and not only the use of open design principles. And here is another big question. So what is replicability when applied to the open healthcare context? This definition might be trickier to define than the previous one. So there are different aspects we should consider for that. The point is not only achieving function and hardware version in their respective settings, but also avoiding adverse side effects during their use. This can be done thanks to the validation and testing of the device and its replicas. We should also meet satisfactory replication despite the variability embedded in distributed open source products, such as modifications in their design, variability in local materials, and manufacturing processes. This last part is also still a topic for real-world adoption of open source assistive devices, and that is also part of what this presentation is focusing on today. So today's aim is to reflect on the replicability challenges existing in distributed open source assistive technology. And I will do this through an ongoing case study from our lab. This project focuses on the development and validation of a version of 3D printed forearm crutches founded by the Interdisciplinary Development Initiative at Western University. Our lab is currently working together with other departments and groups at Western, merging each collaborator's expertise and knowledge to foster the real-world application of such an open-source assistive product. I really want to thank them for all the participation and engagement they are showing in this project. What we are aiming for is to develop an open source 2-pieces 3D printed crutches that should be replicable in low resource settings and in humanitarian context. And for this reason, we aim to achieve some replicability goals. So the first one is optimizing the fabrication of this product on low-cost desktop side 3D printers to reach a broader audience of customers. The second one is to reduce the need for off-the-shelf parts and make this product less influenced by the availability of such components. The third one is trying to rely on locally available materials, or even better, if possible, discarded parts for non-structural part of the product. Finally, we aim to meet the standard load-bearing requirements for safe use of standard crutches, paying attention to safety when the user is using this device. The development workflow can be divided into different steps. We designed the first version of the crutches during the first design phase, and we optimized its fabrication as a second step, reducing time and material use. We then tried to study the replicability of these parts by considering different materials and 3D printing setups. We assessed all these different combinations through mechanical tests, which were useful to improve and further modify the design, make it safer and suitable for use. Now we are trying to replicate the mechanical test on this new version, keeping the different combinations of materials and setups. And at the same time, we are working on alternatives to some less available materials or more affordable options. Focusing more on the development and validation of the crutches, we are working on a version that is made of a 2-piece 3D printed forearm upper element, this to facilitate the replication of the 3D printed components with low-cost 3D printers. The assembly can be divided into different components using 3D printing for most of the parts, either with rigid or soft materials, and only a few extra off-the-shelf components. We included parts made of PETG and TPU filaments for rigid and soft parts of the product, And then we selected wooden dowels as the main connection parts, allowing for customizable lengths. And we added wood screws for the assembly, the on-the-shelf part included in this product. All the 3D printable parts fit the volume dimension of desktop-size 3D printers, making the replication easier for users with small format 3D printers and at the same time allowing for multiple part 3D printing if using large format systems. The second step was then optimizing the 3D printing settings. So what we did was print full solid parts made of PETG to ensure the mechanical requirements we needed for safe use of the crutches. We also considered other aspects during the previous phase, which we checked when printing. First, we avoided the use of supports thanks to the design shape and selected building orientation. And we also tried to suggest a preferred building orientation through the design shape of the 3D printer component. For instance, specific flat base areas or similar aspects, adding a further way to control replicability and guiding the user. On the one hand, this was also useful to reduce the time used for printing the different parts, the material used, and the waste. On the other hand, these choices make the part easier to fabricate by non-expert users. Then we tried also to work more on the replication aspect connected to the 3D printed parts, and we considered using different materials, filament and qualities, and also different 3D printed formats. What we did was select one material for the structural components, PETG in our case, and print them with both virgin matte filaments and recycled ones. We did this either with small-sized 3D printers, such as Prusa MK3S, and large format 3D printers with building plates suitable for printing multiple parts at the same time. These trials resulted in 4 different batches of samples, where batch number 1 uses virgin filament and small-scale 3D printers, batch number 2 switches to recycled PETG, and the other 2 batches are focusing on large format 3D printer, where batch 3 uses virgin filaments and batch number 4 goes back to recycled ones. These parts also correspond to 4 batches of assembled crutches that we assembled to refine the assembly procedure and perform mechanical tests on this version. We first referred to the right standard for the test, and we selected the ISO standard available for working products to be used with one arm. We then used a custom setup to simulate the anatomical structure and movement of the arm. This setup was previously developed by our lab in another publication, and we adapted it for our current configuration of the crutches, replicating the natural posture during use, thanks to simulated joints of the forearm. We then started to test the applied and increasing load, as you can see from the video. And we did it for each of the 4 batches of samples that we have, which means 5 crutches each. So we tested around 20 prototypes in total, trying to reach the maximum load. In doing this, we also analyzed the maximum load achieved by the different materials and 3D printer combinations and the failure types, which were quite different for each batch, but should ideally meet the standard. So we aim to support 100 kilo without failing for 10 seconds to meet the standard. These results allow us to make further modifications, which first means modifying and redesigning the critical components leading to failures, in our case, the handle, to achieve the target standard, so 100 kilo without failing for 10 seconds. We then reprinted the new parts and further tuned the parameters to reduce any inconsistency in the material flow and ensure 100% solid parts. And finally, we reprinted the parts with virgin and recycled materials using both small and large format 3D printers according to the previous batches. We are now doing the mechanical test on these new prototypes, and they look promising because we are getting to the standard requirements for safety, and the replicability of our part is good because we are observing similar failure modes on the sample, and these also highlight some patterns and supporting replicability. We are also working on how to replicate this product in local low resource settings by providing alternatives and redefining our current design. For instance, some ongoing tests aim to avoid the use of TPU filaments, which can be tricky to find in some contexts. And for this reason, we are also considering already available materials or discarded parts for non-structural elements. For instance, we are trying to develop one version using discarded bike tires for the padding and grips, also simplifying the 3D printing process for non-expert users. As far as now, these ongoing activities have led to an important takeaway about the replication challenges behind open source 3D printed crutches. Such challenges should be considered during the whole design process of the crutches. And for doing this, we should find new ways to assess the variability connected to their distributed application and simulate them during the design process. This concept can also be extended to the open source healthcare context, leading to the main takeaways of this presentation. And according to this, distributed open source assistive technology needs to include replication assessment during the design process, considering potential variability connected to the replication context of the product. This means that we need to design and share specific procedures and methodologies to be included in their development. Of course, replicability is also affected by different factors. Study from our lab highlights some key aspects that can be seen as a starting point for structural replicability assessment in the context of open healthcare products. Considering materials and technologies, we should consider the local availability and affordability of materials and parts, and the same should be done when choosing manufacturing technologies. In general, the target is an adequate quality level of materials, parts, and technologies to ensure both functionality and, most of all, safety and no side effects during use. Focusing on designing replicable products, we should rely on available and affordable materials, parts, and technologies as much as possible, designing and keeping in mind possible alternatives without affecting the main function and safety. The extent to which products are designed to be easily replicated guides the whole design process and should consider non-expert user as the main target for replication. This approach can help increase the overall quality of replicas by simplifying their replicability. Back to the crutches, our next steps will be to conduct user tests, creating detailed replication guidelines to be released, and to support the replication of the crutches in a real-world local context. Finally, additional factors affecting the replicability of distributed assistive technology should be detected and studied future projects, including how to assess them during product development. So what can we do to address replication challenges in distributed assistive technologies? I would say this is an open-ended question that we should address altogether. So thank you for your attention, and thanks to the collaborators involved in this project and the participant organizers of this event. Feel free to follow us and connect if you're interested in our work.
We're going to head to lunch. It's going to go until 1 p.m. So just come back to the room, take your stuff, leave it. We'll be serving it right outside the doors. And yeah, enjoy.
So what we did is essentially bring this model. I'll talk about it. And you can, you can snip off these like little tabs. And so that is exactly what we want to have. Because everything is, saturation. Nobody does it. That's just part of
Okay, everybody, may I have your attention, please? Please and thank you. So we are about to get started and head back into some of these talks. I am Ibn Zone. Again, I will be your MC for the rest of the afternoon. I have the unfavorable task of following after a phenomenal MC in Heron, which let's give a round of applause for them. Yes. So I have the unfavorable task of following up with your phenomenal MC Heron, as well as following right after lunch. So stay with us now. But we do have an exciting talk for you coming up. So next up is David A. Gerada and Dr. Eisen Chero Kassin. And so David is a second-year medical student at University of Texas Medical Branch prior to medical school, where he worked in the biotechnology startup space as a laboratory manager and a researcher. So he will be giving a virtual talk entitled Cranex, an efficient, portable, open source, and all-in-one multi-tool for cranial nerve and sensory examination.
Hello, my name is David, and it is a pleasure to present here at the Open Healthware Conference. It is truly a fantastic opportunity to be able to see what like-minded people are innovating and present to them what we have been working on. So without further ado, I would like to present to you Cranex, a compact 3D printable multi-tool for comprehensive cranial nerve examination. Like I said, I'm a second-year medical student at the University of Texas Medical Branch, and I earned my degree in biomedical engineering from the University of Texas at Dallas. My wonderful collaborator and mentor is Dr. Eisen Chassin. She's a medical prototyping lab lead and is assistant professor in the Department of Pathology. Prior to discussing the prototype, I would like to discuss what the cranial nerve examination is. So the cranial nerve examination is a neurological fundamental assessment that is performed by various physicians, such as primary care, neurology, ENT. This is also something done in the emergency room. And it evaluates the function of 12 cranial nerves, focusing on cranial nerve 1 to cranial nerve 8 in routine exams. What are the cranial nerves? There are nerve fibers that extend from various parts of the brain and it allows us to see the health of the brain. So let's start with cranial nerve 1, the smell. There's 4 cranial nerves involved in the eye. 2 is specifically the eyesight. Here you have the optic chiasm. So for instance, if a person has a pituitary tumor, which will sit right around here, it will interfere with cranial nerve 2. And that's something you would be able to spot in a cranial nerve exam. Oculomotor, trochlear, and abducens nerves, they are all in charge of cranial nerve movement. And they're coming from this part of the brain, which is the reptilian brain. And not only does the reptilian brain take charge of the functions in the head, it also takes charge of many of the autonomic functions in the body. So if there is something going on with the pons, the medulla, or the midbrain, which is involved in functions like breathing or something like that, one would start to see deficiencies in the cranial nerve exam if there is something going on here that would also interfere with a cranial nerve fiber and its origin. Then we have the trigeminal nerve, which splits off into 3 different branches in the forehead, the maxillary area, and the mandible. People who have had chickenpox eventually develop shingles, right? And it's because the virus, once one has gone over the chickenpox, it likes to hide in the trigeminal nerve ganglion, and it shows up later as shingles, irritating along the face. And then lastly, you have the vestibulocochlear, which takes charge of the hearing and balance. So then, how are these nerves tested? Cranial nerve 1, of course, is with scented material. Sometimes people like essential oils, coffee grains, an alcohol prep pad. Cranial nerve 2 is something that's routinely done in optometrists' offices with a Snellen chart. So that's with a big E, and it just goes down line by line with smaller letters progressively. And then cranial nerves 3, 4, and 6 are with tracking an object. If you have ever gotten a cranial nerve exam, it looks like following an H. Cranial nerve 5, which is very important, a cont whisk, a sharp object, and a blunt object. So not only is it, do you feel something on different parts of your head, but are you able to distinguish the sensation type? And then from cranial nerve 8, obviously you have a tuning fork. So these are some of the pictures of the tools that are used. Like I said, this is a Snellen chart. You have your cont swab, which is, we will discuss later how this tool is turned into a sharp and a blunt object, as well as a cont whisk. And then you have here a tuning fork. What are the current challenges? So as you saw in the previous slide, there's multiple separate instruments that are not necessarily always available. Yes, a primary care physician will have access to a cont swab and a cotton ball in their office. But for instance, in the ER, somebody might have access to it, yes, but it's not necessarily always readily available. So that's 1. 2, the materials are improvised. And this is actually how it's taught to us as medical students. We're taught to grab a cont swab with a wooden base. We break it in half. One half we'll use as a blunt object, and the other half we'll use as a sharp object. And then cont balls are made into thinner pieces of cotton that we use as a soft touch. Then from there, there's also portability issues. So the tuning fork that's usually used for cranial nerve exams is actually really large. And then these materials being sparse, again, it makes it difficult to be able to do this in a streamlined, standardized way. Then lastly, not only for cranial nerves, but also for the wider neurological exam, temperature testing is something that's sometimes suggested to be done if materials are available to you. So the way that's done is with tuning forks, because they're cold and they're metal. But if they're used during the cranial nerve exam, then they're going to warm up, and that's going to present a problem to accurately evaluating if the person has the capacity to feel cold or hot wet. So the solution, a 3D printable open source multi-tool for cranial nerve and sensory exams, which will include a light source, tested for cranial nerve number 2, sharp and blunt ends for eye movement also as tracking, sharp and blunt ends for sensory testing in different parts of the face, ball compartment for soft touch, a 440 hertz tuning fork attachment. So this tuning fork is really small instead of the really large one that's used in common practice. And lastly, a retractable Snellen chart. And then ideally, the blunt end also includes a metal heating element for temperature testing. And overall, the goal of this would be designed for efficiency, portability, and ease of use. How do we go about the design process? So the standard engineering design process for any prototype, you begin with a problem, which we have already stated. We brainstorm in a piece of paper, talking about different ideas on how to put all of this together and solve all aspects of the problem. Then we move on to designing, from the brainstorming, designing and making a plan. This is where 3D renderings start coming into play. Then we build a prototype. From the 3D renderings, they're printed. Our initial prototype had these dimensions, and then as we used it and tested it, we evaluated, improved, and printed it again, and so on and so forth. A lot of people say that prototypes aren't truly done. There's always some way in which you can inform yourself and you can improve your prototypes. And this remains true with Cranex. So brainstorming and making a plan. This is a picture actually right from my iPad in which I tried to solve each of the individual problems that we talked about. Here we have a tuning fork. I found the smallest tuning fork possible that was still functional on Amazon with these dimensions, and I used that as a model for the dimensions of the rest of the tools. I thought that would be a good idea to make it consistent, standard. Then you have your tool for light, tool for heating, blunt end, sharp end, and a brush, not a cotton ball. So I just want to say this was the initial plan, but you can see it presents some challenges. This is actually much larger once you have it in your hand. This is extra space. That was unnecessary. The Snellen chart would go here, yes, but also there needs to be space where to access the battery on the side panels. And this is the 3D rendering of the more finalized prototype that we have right now. So although it's the same idea, it still looks a little bit different. The design language is a bit different. We have two sides of retractable tools, a sharp end, a blunt end, a cotton ball compartment, and then a light. And here we have the side panel. Other pictures include here, you see on the inside, this is where a battery would go. This is the channel for cables to be able to go to the light, and then the blunt end where we would put the heating element. More renderings. And then here I want to highlight the channel for the cable that would go into the light. And then eventually this part will be modified also to add the heating element. So this is our friend the Ultimaker. Has been a great companion in making all possible designs. And then here we come to the printed design, or the final piece of the design process before we begin to reiterate. So like I told you, the initial design had the tuning fork as part of the retractable elements. And although this seemed like a great idea when drawing up the plan, clearly it presents a challenge. This is too large. It's not portable. It's not efficient. Putting that in a pocket is a nuisance. So then instead of having the tuning fork inside, we decided to put it as an attachment, something that can be snapped on or off of the multi-tool without compromising on the size. And instead of using large AA batteries, then we can use very small ones. Then we looked at this design and said, we can still make it smaller. And we did. But then we realized, hold on, this is a bit too small. The cotton ball compartment is going to lose all of its functionality. And we decided that this size of the cotton ball compartment was the best. And that's why we decided to keep that one here. Then the light source will also have the same size just to give space for wires. But the sharp end and the blunt end, they don't need to be really large, unless we decide to change the setup in case the blunt end with the heating element needs more space. But ideally, probably not. You need to have as least material between the heating element and what's going to be heated as possible so it doesn't get lost. More pictures of the finalized prototype. Here we have the sharp end, the blunt end, the compartment, then the light source, the side panel with channel for the cable, and the tuning fork. Where do we move on from here? So ideally, we want to manufacture this in metal rather than PLA for durability and thermal conduction at the blunt end. We want to add the Snellen chart that we talked about. It's a matter of finding one that complies with our size specifications or simply making one if it comes down to it. And then once all of these things are done and we have a durable device, then we want to put it in the clinic under IRB oversight and see how it performs at the hands of a physician. And then from there, we can get feedback on where to improve, what other things can be added, or what other things are unnecessary. Then we're also interested in open source dissemination for global adoption and feedback. And then lastly, potentially integrating it into medical education and telemedicine kits. If a person wants to do a cranial nerve exam at their home in a telemedicine appointment, this tool with instructions would be a perfect way to do so. It would be standardized, and if globally adopted, it would be something that would be used at the clinic and at the patient's home without having to find a way to standardize scattered materials. Global dissemination has already started. We have put the Cranex 3D printing files, the FreeCAD renderings, and the pictures of the printed design in GitHub. If you're interested, please give it a look. We believe that open source is the pathway to innovation. Many medical discoveries, medical innovations, medical devices have been possible because of publicly available research produced by public institutions like ours. So we're full believers of open source, so please give it a look. And thank you so much for the opportunity to allow me to present, and have a great rest of your day.
Okay. I want you guys to imagine something. You just spend 1 year, maybe 2, working on your next open healthware project. And you already launched it, but it's been 3 months. Now it's been 10 months, but you don't seem to hear about the community like working on it. Like there's nobody contributing to it or like showing progress with it. And trust me, it's not because it's bad. It's more because you just put it out there and you didn't show them how to actually use it. And this is where I come in. I'm Kiara Vasquez, and I am the community and marketing coordinator for the open source leg that is at the University of Michigan. And for those who don't know what the OSO is a prosthetic leg, lower limb prosthetic leg to expand access to research. And overall, like what I want you guys to take of this talk is lessons that the OSL team learned through building the OSL, how you can get your project from going nowhere to actually getting people to adopt it and be using it. And with that, I want to explain to you why being open isn't enough, and it's only the starting point of how you get started in a project. Well, to make this simple, I'm gonna give you an analogy. Baking cookies. When you I gave a list of ingredients to my friend that doesn't know how to actually bake, and I just told him like these are the ingredients and gave him very simple instructions. But I forgot that his oven doesn't actually work. So he actually used an air fryer. So straight up, we have an inconsistent setups. And not to mention, like in the instructions, I forgot to mention that he had to like cool have the butter and the eggs at room temperature, and that he needs to cool the cookie once he makes the dough, and some other steps like preheating the oven. But I already straight up gave him unclear instructions of how to make the cookies. And not to mention, when I gave him the instructions, I told him to use a very specific butter and very specific to use dark chocolate from a certain brand. And he didn't follow through because he just used what he had in his kitchen, which was margarine and milk chocolate. So straight up, he went with what he already had instead of like going out of his way to like buy something, which kind of goes back to like him not wanting to like spend more money and kind of like going to the cheaper option. And since he was baking the cookies like at 1 a.m., he actually didn't have me there helping him because I was already asleep. So the result of all of this is that he burned the cookies. Um, but and this was because I didn't give him a proper onboarding experience. And this is what I mean that when it comes to like providing an open healthware project in general, is that you have to provide a good onboarding experience to your users, because it makes sure that they are able to like use it. And through this, we have to like learn when making an open healthware project is that what challenges are you solving for your users? And for us, it actually meant like stepping back and like learning that there are several amputees that like 5.7 in the US. Well, I might gotten that number wrong, but don't quote me on that one. But anyways, there's several amputees and lower limb amputees that you would have thought that the lower limb prosthetic research would be like expanding fast, but it's not. And what is actually causing this slow progression, first of all, is that every lab has their own prosthetic leg. Like there's not a set standard. As you can see in the top right corner for you guys, the different prosthetics legs around 2017. And not to mention time, like not every lab has the time to actually go around and like building a prosthetic leg, because it could take years. But not to mention, building a prosthetic leg could take over $300,000 to build a prosthetic leg, and this leaves smaller labs out of reach to be able to do this, which in the end results in the prosthetic research community fostering isolation instead of like actually rendering like actually expanding research, which understanding the problem does leads us to, oh, what happened to my slide? Okay, well, this slide was supposed to be about talking about the open source leg, but I can still talk about the open source leg. Which for those who don't know about the open source leg, it's a I already mentioned lower limb prosthetic for research, and we provide hardware, software, and electronics, which helps like making sure that there is a set standard of how to build it, so people can like start just building and being able to compare the research. And then also like with the software, we get people going. And then with our electronic boards that we're starting to launch, and make sure that people have control over their software. And now like people can also build a prosthetic leg quicker, which means like 30 minutes, and they can build it for less than 25K. But let me lay down the groundwork for the OSL. We started in 2017, 2019. The OSL launched the first set of materials. In 2022, we partnered with Humotech, which allowed new users to get easily on board when they could buy a whole pre-built OSL, or like just the materials needed to get started going. In 2024, we started a component-based software release, which meant kind of like Lego blocks, where you could just customize and use whatever you need. And then in 2025, we're focusing on community and making sure that people are contributing, this meaning forks, pull requests, modifications, because at the end of the day, we want to co-create and shape the future with our community for the OSL. And in 2019, we first launched our peer review article with the Natural Biomedical of Engineering, which first introduces the OSL, which also led us to publish the first website that had the information about the project, meaning that you could download the files and get the step files and send it to machine shops so they could like build like the OSL parts for you. And we provided them the first tutorials so they could like build the hardware. But we only gave them the hardware. So they had a prosthetic leg and they couldn't get it running, because now it's like what if they don't know how to use the software? So we actually had to also set up a Raspberry Pi, which automated the network connection by sending email IP address. And then we also uploaded Python library with it in the OSL website, and included tutorials so they can follow up and make sure that they were able to get unwrapped and get the OSL on use. And with this, with the hardware and software, we started to see research labs adopting and running their own experiments and publishing papers, which by the end of 2021, we had around 10 research groups, which meant that we were going somewhere. We were being able to get reproduced and have people use the OSL. And it was no longer our project. It was a project for the community. And around 2021, through our community feedback, we learned that we had to make it more simple, more portable, and enhance the technical capabilities, which meant simplifying the three-stage to a single belt driven transmission, reduce the hardware cost to simplify the assembly, and then also double the ankle range of motion, and a few more other things that you can learn about in our website. And then this turned out to be OSL version 2, which made it lighter, cheaper, modular, and quicker to build, which comes back that now you can build the prosthetic leg in 30 minutes, all while maintaining like the high performance of version 1. And it took less effort for people to build, which meant a quicker onboarding experience. With that, we did actually update the website, which consisted of updating new files and step files so that they had like versions 2 of the OSL, but it also meant that they needed new tutorials, so we uploaded new tutorials. sorry. We also updated the version, the software, but the slide is not popping up. But anyways, with the software, we updated, we switched our GitHub tools to, well, we switched the Raspberry Pi to like a GitHub tool, so like we could constantly update it for our team, for the users, so they don't have to be constantly going to our website and getting the new GitHub tools. No, Raspberry Pi setup, and then we also launched our Python. Instead of being hosted in our website, we switched it to PyPy, and now users could easily download it just by running a pip install. Which, as a result, by having the Python library in PyPy, we got over 4,000 downloads the first year, which actually meant that we were getting users apart from the users from the OSL community. And it was nice because at least we were getting contributors who were using our Python library beyond of what we were expecting to. And we also moved our design files from SolidWorks to Onshape because it allowed for real-time contribution, and it kind of also has built-in control, and it's a cloud design platform. And through this, we also kind of focus on designing like openness, which meant like providing tools that users can use, and like it meant like launching our first DAQ board, which you can scan to learn more about it. But it was also like a way for our users to contribute back to the community, and that was possible also by how we manage our platform, which it skips a slide, but in the previous slide, it was supposed to show how we have funded the project overall. And in 2017, we had our first grant, which was an NRI grant, which helped us build the OSL version 1. And then like in 2020 to 2022, we had our next NRI grant with the NSF, which helped us fund OSL version 2. And then by 2022 to 2023, we had our NSF post grants phase 1, which helped us build the community. And then we currently are running on NSF post number 2, which is more community driven focus and making sure that the community is more given. Okay. And you might be wondering like why focus. Sorry, I keep looking at the slides because they're the wrong slides. But anyways, I'm gonna work without the slides. But like you might be wondering like why community focus? Well, we ended up as of right now, we have 25 institutions using the OSL, which meant that we are getting more users, which is more contribution. And with that, it also kind of meant that we were getting more engagement. As a result, the OSL did onboard more people, and this meant that the OSL got Center, and through Center is the project lead manager for the OSL team that kind of just makes sure that there's any bugs, updates the system, and just kind of like controls stuff like the software and like technical aspect of the team. And then afterwards, like the team can only go so long with just improving on the technical aspect. So that's when they realized, oh, they need a community and marketing manager. So that's where I come in. And you might be wondering, why do they need a community and marketing manager? Well, first of all, like in the marketing aspect, it increases visibility and adoption. And when this is important in the simple aspect that through this, it also attracts funding and partnerships. And it also means that through bringing funding and partnership, we're accelerating the growth, and like by accelerating the growth of the project, we're able to create a bigger brand that people will trust. And we kind of also want to make sure that in the community aspect, we also want to make sure that our users become contributors, that they're not just using the OSO, but also helping build back the community. And we want to make sure that it creates a support network, that even when we're not there, like our users are contributing and helping other users out to questions they might have. And overall, we want to help by me being in the role, we want to help generate a feedback loop, understand what challenges users are facing, and being able to like help them out, answer like questions they might have, and improve the overall retention that they might be experiencing, and building long-term sustainability for the project. And we focus, like my first role was to focus on the branding guideline, which you might think like, oh, why would I, what would you focus on the branding guideline if it's just logos and colors? Because that's all I have in the screen right now, but it's more than logos and colors, believe me. It's an identity. So when it comes to branding, new branding is that we're able to get a more recognizable face, and it means that we're more credible, and it's and it makes people feel part of something, because we want them to feel like the community is growing and that they want to grow with us. And it also means that we are growing outside from just being a project that started in a university lab, because even though we did start in a university lab, we're more than just that. We're an ecosystem, and we want to drive recognition and expand our audience. We want our audience to come outside from just researchers and students. We want people in the industry and people who are hobbyists to contribute back. And we want to help build in connections so that they feel attached to us. And we want to make sure that we're different in a crowded place, and make sure that we enable growth in our future. And this is where our branding identity comes in. This is our logos that we designed, and we decided to go with like full open source leg, and then like the open source leg and 3 layouts, and then the OSO. And the reason we chose this icon for our branding was simply in the aspect that we kind of wanted it to represent a prosthetic leg, in the sense that it kind of looks like a prosthetic leg if it's like that, like it's the foot and then like the upper. And then like we also kind of wanted to be like OSL like hidden, so like it's an O, and then like if you were to draw a line, it would be like an S and then like an L, so it kind of has the OSL hidden. But we also kind of like left gaps because we wanted to show that we're open to the community. And as for the colors, how we ended up choosing them is that we felt like a lot of tech companies go for the blues, blacks, or whites. We kind of wanted to stand out. So, and we wanted to also make it welcoming to new users, because we don't want an undergrad to be like a freshman in undergrad seeing our page and kind of be intimidating and not wanting to join the OSL. So that's where our color choices come in. We chose the Mirando and Vista Blue, which makes our website more welcoming. And through this, we also created some logo placements, which are not on the slides, because I just realized these are my old slides. And then the logo placements, we make sure like that users know where to put our logos. And we also put logo misuses, which as we want to make it more professional branding, we don't want people to misuse our logo. And through that, we also created branding assets, which are currently not on the slides, but since they got launched on Tuesday, but will soon be integrated in our upcoming website. And through that, and we're gonna start using them to like put information and like making sure like we have a cohesive branding. And we also created like we got a font that will go all throughout the OSL websites, posts, PowerPoints, and everything. Like we are making sure that our branding is very cohesive. And then we also have OSL business cards, which currently don't are not in relation to the new branding, but we're updating our business cards soon. But we're like just making it step by step. And then we also updated our website. Whoops. This is what I mean that my slides didn't get updated. Nope. Okay. Oh well. These are, but anyways, we updated our website, and like we're updating our website for the fourth time, and like with the new website, we made some few changes. And first of all, I am sad that you guys can't see the website because it looks really nice. But in the new website, it has all the like the main components of how to build the OSO in the homepage. So that means having the CAD, having um, the hardware, the robot CI, which is the GitHub, and then also like the it leads you to the pipeline, and then it also leads you to the CAD files, all in just the landing page of the OSL. And then it also has like when you're building the hardware, it also has a tracking. So like you don't have to worry about. Yeah. Okay. And then like the updated website, like you don't have to track it. And then it also shows users like how like the OSO is growing, meaning like the how many people are using the GitHub, how many people are viewing the website and stuff like that. And also it gives users a tool where they are able to like post where their there published articles about relating to the OSL, and through this we also updated our forum. Our forum, like right now, is hosted in our website and it works, but there's currently an issue that not new users are not able to join the forum. And through this, we decided to change to Discourse because our current forum also doesn't give notifications to our users, so that will take around a whole week or maybe even 2 weeks just to hear back. And hosting within Discourse, it means that we can better categorize our conversations for our users and create subcategories. But we can also just give them rewards for interacting with our community and kind of just be like, oh, congrats for getting 100 likes, here's a little trophy. And then also like they can respond through email, so they no longer have to come to the website and like search and just to ask questions. They can respond through email and get email up notifications of what's happening in the discourse, as well as get a quick summarize of like everything that's happening in the discourse. And through this, we also created social media pages as we wanted to make sure that we were reaching people at where they are, which you can follow us. You can follow the open source leg at open source leg in LinkedIn, Facebook, Instagram, and X. And we started posting like every week, and now like we're trying to increase our posts to twice a week. And I keep track of all the posts by having an Excel sheet, meaning that you guys can do it too. And within the Excel sheet, it just kind of keeps tracks of making sure that every post is posted, as well as that it has a proper caption and it kind of has a checking experience. And then currently our social medias, we're not doing paid promotions. We are just doing organic growth. And our LinkedIn has actually experienced like 365 followers being open since April, and like just in the past 90 days we haven't gotten 98 followers, which means 1 follower per day, which is pretty good. um, and then we have also seen that Facebook has worked pretty well for us, and like compared to Instagram, just because Facebook group has like the communities that we can share within groups. And we're not just building for the community, we're also just trying to build lasting connections with your users. We are creating community spotlight, sharing them in our socials, newsletters, and our discourse. And also we're making surveys to make sure that our questions that users have are answered, and running feedbacks, survey feedbacks, where we learn that some users feel like the tutorials are not enough and kind of challenging to understand. But where we headed on the long term is that we want to co-create OSL version 3, which means a design challenge. And we also want to get our community more involved, and we're gonna share more resources and tutorials, where I'm gonna get started, and then also afterwards we're gonna just keep our community update. But overall, like, just thank you, and thank you for all our users and people. And sorry that my presentation slides didn't pull through, but I hope you guys enjoy the talk. Thank you.
Let's give it up again for Kiara. And so now our next talk will be a virtual talk by Arti Ahu Awala, alongside Carmela de Maria Arti, who heads the Ubora Association. The association manages the Ubora platform for collaborative design of safe, open medical technology. We are incredibly excited to have her share her virtual talk named Ubora Platform, Collaborative Design of Safe, Certifiable Medical Devices for Health Equity.
Hello everyone, my name is Arti Alwalia, and I'm going to talk to you about the Ubora platform for collaborative design of safe, certifiable medical devices for health equity. So I'll start off with a little bit of background. Nearly 20 years ago, when I was much younger, I was funded by the EU, the European Union, to help develop core competencies in biomedical engineering and clinical engineering in the Philippines and Indonesia. This project was focused on developing teaching courses at university level for biomedical engineers in these two countries, because it was recognized then in Asia that there was a lack of capacity in these areas, and this was holding back development in healthcare systems. Thanks to this work, I was invited by the United Nations Economic Commission for Africa to a summer school that they had funded on developing biomedical education programs in African universities, because they recognized that health in the system, health in the countries, is the way towards wealth in the countries. There were many like-minded people at this summer school, and together we decided to create what's now called the African Biomedical Engineering Consortium, which is a consortium of African universities which work together to harmonize quality education in biomedical engineering as a method of developing a new professional healthcare sector for improving healthcare outcomes in Africa. Thanks to this, we got together with the ABEC team to apply for funding again from the European Union to create a virtual platform for the co-design of open source medical devices to address these global healthcare challenges, the lack of equity in healthcare across the globe. And the platform is now managed by the Ubora Association. So what is Ubora? Well, it is a platform, as I mentioned. It's a virtual infrastructure, and it's also the community that manages and uses the platform. And it's for helping people co-design open source medical device technologies, focusing on the safety of the devices right from the beginning. So safety and efficacy are two key words in our philosophy. So medical devices, as you all know, are intended to prevent diseases, diagnosis, and they're also used as support systems for people who are unwell. And they can be very, very simple, or they can also be very complex and very invasive, but they must all be safe and effective. And it's really important that we deliver safe and effective quality medical devices, high technology ones as well, to everybody in the world. This is one of the UN Sustainable Healthcare Goals, equitable healthcare, through access to quality instrumentation, which is now used all over the world by doctors. They rely on quality instrumentation. There is a problem, though, in low middle income settings or low resource settings, because a lot of the equipment is generally donated. Very little is purchased on site, but in fact, most of it ends up in what's known as donation junkyards, because people don't know how to use them or to maintain and repair them. So the problem is not just the lack of money, but it's also the lack of expertise, lack of sufficient staff who know how to run and manage the equipment. There is also a problem of lack of spare parts, and also the lack of reliable electricity and running water. Most of these devices are actually made and designed in countries where everything runs perfectly, and then they come to be used in situations where it might not be so. So these challenges could be addressed by using an open source approach. So that is developing methodologies where you share the source code and design specifications, and you also allow people to distribute and modify, and also by enhancing local production, so local materials, using local capacity to make and repair, and definitely through targeted training programs, because quite often in low resource settings, there's not, as I mentioned, adequately trained staff. There isn't sufficient capacity. One of the challenges of applying this type of approach in low income settings or developing countries is that the regulatory framework that people normally use is the European one. It's a very well-known regulatory framework, which sometimes is not really strictly and directly applicable in low resource contexts. One could develop solutions through the frugal innovation methodology, and this is one of the key concepts in the Ubora platform. So the Ubora platform can be reached using this link here. So when you go to this link, you sign up to the platform, and you come into the Ubora system, which basically operates within the first steps of the life cycle of a medical device, which is where most of the costs are centered. So developing medical devices is actually very, very costly. And a sharing approach, as well as an open source approach, could substantially reduce these costs. We do focus very much, as I mentioned, on safety by design, and so the platform also has expert mentors who contribute to the design process. So we empower collaboration and we stress safety right from the start. You go onto the platform, it's divided into different areas, different tabs. So the first one is clinical needs, and then the development of the projects, different resources for supply of materials, for example. And then there is the community that you can refer to for expertise. And then there are various administration tools that the management group might need. So the clinical needs is probably the most important and the most innovative part of the platform. So this is the one where people try to identify needs by coming together as a community. So it's both engineers and clinicians as well as patients. And then we have the part of project management, which is the management of the different devices that one might come up with in the initial needs through the initial needs process. And then you go through a device classification process, which you classify using a decision tree with 30 different questions, and that helps people classify their devices, and thereby be able to understand which are the standards and the regulations that they need to use in order to be able to develop and then implement their biomedical device. You go through then the phases of concept design, and prototyping, step by step. So you get followed through, and obviously at all steps of the process, you can access expert opinions and people who know about medical devices and know also about teaching and design. And then finally, we've got the process of the pages or the packages of implementation, operation, and finally the project closer process, which involves actual development for manufacture and sale. There are also many resources, as I mentioned. So Ubora is generally very widely used as a teaching material, both within Europe and Africa. And so we have slides, handout notes, etc. We have several tutorials and building process documentation that students in classes can follow through. There's also a user manual and a developer manual. And then, as I mentioned, there is a large community of over 500 users, 400 to 500 users, growing continuously. And I just wanted to mention some of the success stories that have come out of Ubora. So a couple of companies have adopted our open source automatic defibrillator within Italy and within Europe. There is a solar power autoclave. There is a baby warmer that has been sold now in Uganda. There are walking frames, for example, in carbon fiber, which can be used for the elderly, which are very low cost and very light. And these are completely open source and can be easily used and distributed anywhere where they're necessary. The other success story that I mentioned is the automatic external defibrillator, which is a class 3 medical device compared with the first one. And this one is now currently being marketed in Italy and within Europe. So this medical device was developed completely using the Ubora platform. The other success story that I should mention is also Palp Breast, which is a bra used for breast examination. And this is a completely wearable and safe class 2 medical device, which can be used instead of self-examination, which many women tend not to do for lack of confidence. Ubora has also been very successful in its outcomes. So apart from the development or the setup of ABEC, we've also been able to gain funding for a biomedical engineering mobility program across Africa, where staff and students were exchanged, and also ABEC and ABEC came together to develop a common core curriculum, university curriculum in biomedical engineering. Another important outcome of the Ubora project is a new project which has recently been funded by the Italian government, which is called the Afya Moja project, which means One Health in Swahili, and it promotes the shift from capacity building to capacity strengthening by working together. So not just building new capacity, but also building on strengths that African people and African countries definitely have, but of which are not valorized. The project actually spans across 4 disciplines, not just biomedical engineering, but it also encompasses medicine, veterinary medicine, as well as agriculture and nutrition. So the Ubora platform is still going strong, and I do invite you to go and have a look at it. And I'd like to thank you very much for your attention.
Again, Okay. So with that, we're going to have a small change. And so we're going to have Jen Wilson's talk next, but that's going to be virtual. And so Jen Wilson started as a volunteer with GLIA and then became the Director of Manufacturing and Design in 2023. In her role, she manages the design and manufacturing of GLIA's medical devices, as well as updating their GitHub repository and making the instructions for their devices as comprehensive as possible. So please give her and her talk a loud virtual high five and hand clap. And her talk is entitled The Democratization of Manufacturing, Sharing is Caring.
Hi, I'm Jen from GLIA. I'm the Director of Manufacturing and Design, and I'm here to talk to you about the democratization of manufacturing. Sharing is caring. Okay, oh my God. It's been a bit of a crazy day, but I'm going to talk to you about how GLIA connects with others around the world to empower them to make gold standard medical devices at a fraction of the cost. That is what GLIA does. And I'm going to talk about our devices. And as I talk about the devices, I will talk to you about how community is involved and how we're networking with people all over the world to help empower communities. So I'm going to talk first about the stethoscope. This is our signature device. This was the first device that GLIA manufactured. Dr. Tarek Lubani, who was working in Gaza in 2012, noticed that there were emergency room doctors that were putting their ears to people's chests. They did not have access to stethoscopes. When he was back in Canada, he saw a toy stethoscope that his nephew was using. He tried it out. He thought, oh my God, this works. And not too bad. Of course, needed improvement. So thus the GLIA stethoscope was born, 3D printed. Not the tubing though. The tubing has been acquired, and it was originally tubing that you could find in a pop dispenser. So it was always in mind to design for low resource settings, materials that could be easily found around the world. So the GLIA stethoscope was born. In 2021, we partnered with Make a Medic, which is an organization in the UK that donates things to medical students to help them. And so we distributed 200 stethoscopes to graduating med students in Kenya and Zambia. And in 2022, 60 students in Uganda got our stethoscopes as well. So this is empowering those medical students in those African countries who do not get stethoscopes. I mean, here in the West, it's easy to get stethoscopes, but there not so much. But these work as well as the Littman Cardiology 3 stethoscopes. You can go to the glia.org website, devices page, stethoscope, and you can see a link to the +1 article that was published about that. So this stethoscope has been really a keystone in connecting people around the world to empower them. Not only have we partnered with Make a Medic to bring stethoscopes to graduating med students in African countries, we also collabed with MedLink in 2022, which is where med students connect with Indigenous youth to try and get them excited about health education, to see if they want to get involved in health education. So a couple of med students at Western connected with me. They went up to a camp up north where there were Indigenous students, and they all got our stethoscope, and I helped them assemble it, and they all got very excited about it. And hopefully, you know, it inspires some of those kids. Certainly in medical education, the medical sphere, there are many, many ways that you can go. One of them is in engineering medical devices. So hopefully some of them got inspired. In 2022, we also had one of our largest stethoscope distributions to universities in Southern Ontario. We distributed 600 stethoscopes with the help of students from Western, from U Ottawa, and from U of T. And U of T has really picked up the ball, and they started their own stethoscope distribution. They get funded by the school to distribute a certain amount of stethoscopes to first-year medical students. They print the 3D parts at the Apple Lab at U of T, which is the, oh my God, what is it called? Hang on one second. The Advanced Perioperative Imaging Lab. My God, sorry. That is a lab at U of T where they scan internal organs and 3D print them. So our students at U of T 3D print these, they bring them back to London, and we assemble them in London so that it's under the MDEL, which is the Medical Device Establishment License. It is equivalent to the FDA. There are 4 main licensing bodies in the world: the FDA for US, MDEL for Canada, there's an EU licensing body and an Australian licensing body, and they usually cover the whole world because those are the richest nations in the world and they can afford to have licensing bodies. But most of the world knows that if it is manufactured under one of those licenses, it is a gold standard product. So in order for a device to be under an MDEL, which means that it is able to be used clinically in Canada, the U of T students have to bring those parts back to London because the MDEL license is specific to the manufacturing location, not necessarily to the device. So yeah, that's another way that we've empowered the community by bringing in med students from Ontario, having them share our work with first year med students and get them excited about, you know, what's possible in the medical system. So a couple of really amazing stories about the stethoscope. There's a doctor in Hawaii, Brett Carey. He's an orthopedic surgeon, or maybe not a surgeon. He's an orthopedic doctor who does 3D printed hand splints. He also teaches kids. And a lot of these kids come from low resource settings near Hawaii, like the Marshall Islands, the Republic of Palau, and the Micronesia area. And so when he's teaching these kids, he finds that they often feel kind of guilty for leaving their communities. They want to give back somehow. So when he has them print and assemble our stethoscope and then test it against cheaper stethoscopes on the market, and they find out how well they work, they feel like they can send back this device that they've made back to their communities, and it will help their communities. So it gives those kids an incredible self-reassurance that they're doing good work and giving back to their communities. Also in 2023, we partnered with a Boy Scout troop in New Jersey to print stethoscopes. They partnered with Rutgers U Makerspace, and they made stethoscopes for Doctors Without Borders and for the Ukraine. So again, this is all about connection. This is about connecting with communities and getting them to feel empowered, like they're giving back, like they can help the world in some way. And because our devices are free, open source, online, on our GitHub repository, anybody can do this. So they feel empowered to make a device that works as well as it does, and to give back to the world in some way. So a very obvious way that we connect with people are right in our community in London. There are a lot of people who are Arabic that are of the diaspora who feel very helpless about what's going on in that part of the world where they come from. They want to give back, they want to help. I bring them into the lab. I get their hands into the projects. So one of the biggest projects that we've been doing is the tourniquet project. When I came on board with GLIA, this was the project that I was mainly involved in. This is a device that was created in 2018 during the Great March of Return. Tarek Lubani and our team in Gaza, Dr. Alatar, Hanan, and Badr, helped develop this device on the battlefield in Gaza. It is a really interesting device in the sense that it is being used under not ideal conditions where you're panicked, where there's chaos, there's blood, and you need to be able to work this device properly. So because it was tested on the battlefield, we believe that it is an effective device. So when the Gaza war started in 2023, we redirected some funds from a project that was already going, which was now no longer able to go. We redirected those funds to make tourniquets in Canada for Gaza. They were usually only made in Gaza. And so I've been a part of this project to create 2,000 tourniquets to get to Gaza. We've sent over just a little over 500 so far, and the rest we're going to get them in when we can, as soon as possible. But the Canada office started making the tourniquet for the Ukraine war, actually. So that brought in a couple of volunteers that are key in this project right now. So again, connecting communities around the world. Adam Papanda got a whiff of this project probably from online, seeing a free and open source tourniquet. He came on board as a volunteer wanting to get involved in making tourniquets for Ukraine. He is now the director of the Poland office. Victoria Jacqua from Open Source Medical Supplies from the US came on board. She now runs this project. And both of them are really, really key to us. Victoria connected us with an open source lab in the US, Public Invention, and they funded open source tabletop injection mold for Poland to make injection molded tourniquets, because when we started making the 3D printed tourniquets for the Ukraine war, we realized very quickly that they were not accepting 3D printed tourniquets. The reason why is because they were getting sent 3D printed tourniquets from all over the world, and they were not quality. Funnily enough, Tarek was going to Gaza just after that war started and couldn't get in, and so he diverted to Ukraine and went and saw one of the tourniquet testing centers. So it was very interesting information that he gathered. So Adam started making injection molded tourniquets with an open source tabletop injection mold that was funded by Public Invention. That connection was made through Victoria Jacqua. Again, this is all what I'm talking about. We are connecting around the world. We are sharing information because we're open, we're transparent, and we want to learn, we want to make things better. That is sort of like the open source philosophy of the world, is to do that. So yeah, that is an example of how that is all working. Another couple of examples are that Victoria also connected us with an open source engineering lab right in our city, the FAST Lab, which is what does FAST Lab stand for? Hang on. Oh my God, all these acronyms. It stands for Free and Appropriate Sustainable Technology. It's an open source lab at Western University run by Dr. Joshua Pierce. And she connected us with him, and so a tourniquet tester was born. This is a device that does not exist in the world other than behind paywalls, proprietary tourniquet testers for big corporations that make a lot of profits off of tourniquets that they sell. So as an open source company, we want to do everything open, so we partnered with their lab. They made an open source tourniquet tester, first one in the world. I was approached by some high school students who do robotics in San Diego. They wanted to help GLIA in some way. I think they wanted to help with tourniquets. The thing is, we don't usually have people from not in GLIA 3D print stuff for us, because then it's not under our MDEL license, and everything that GLIA produces and sells or donates has to be under that MDEL license. So instead, I had them make a tourniquet tester. And so now there's another one out in the world, and they have tested it. They have gone through the assembly instructions that were given from the FAST Lab. They have found some errors in those instructions. They want to improve the coding for the electronics. And so this is all, again, a part of connecting and empowering everybody, empowering the students to make something that's really cool and that works, and then to give us feedback to improve the assembly instructions so that that open source information can be improved for anybody in the world who wants to make a tourniquet tester. So again, another example. Recently, I was approached by some more high school students in California. Actually, they're really inspired to do things. So there's a group in San Jose that wanted to help us, and they wanted to help with prosthetics. So I don't have any prosthetics to show you. We partnered, we had a grant through the Frugal Biomedical Innovation Group at Western University to work with a university in Ethiopia called, oh my God, what is the name of it? Bahir Dar University in Ethiopia, to make upper limb prosthetics. So a couple of guys there have been 3D printing them and gathering all the information on the printing specs, and then getting volunteers and how it's fitted and how it works in the community, how it's accepted in the community. These are all the things that they're learning. And so these kids wanted to be involved in prosthetics. So the one thing that I had them do is design a model, and they're going to print it in TPU, which is a flexible 3D printed plastic, which is sort of like a precursor to prosthetics. It's an elastic that goes around your hand so that you can hold various implements for people that do not have grip. So, you know, again, there's always room for people to come and help, you know, give their input, to try things out, to feel like they're helping the world in some way. And just through the connection and the community, I think that is how that all works. Let me just go back up here. There has been a 3D printed walker that was developed by the FAST Lab at Western University that we're working on right now to help out with our Gaza office. They have made a prototype. I'm helping them with that in terms of assembly instructions. That's really my role at GLIA, is to manufacture the devices, assemble the devices, but also gather all that information together and make it as comprehensive as possible so that people can understand it and so that it's easy to follow for anybody in the world. So we, you know, worked on the tourniquet assembly instructions. It's a pretty intricate device in terms of sewing. And, you know, it's been translated into, I think, 5 different languages so that people all over the world can make this. Another device is our otoscope. We had some students at Trent University in Ontario do a tabletop study against the Welch-Allen otoscope. We're working on a paper right now with the FAST Lab to have that published. And we found out some things. So because Tarek is an emergency room doctor, he used one of our stethoscopes and said, it's not bright enough, just from experience. And so we changed the 10 ohm resistor to a 2.7 ohm resistor. He also found out that a colored head actually changes the color and messes with the optics. So we painted it black inside, and now we're exclusively printing black heads for the stethoscope because of that. And again, it's all about being transparent, being open, accepting information that can improve the device. That is what open source is all about. And yeah, community-wise, we had a renal physician develop this little device, which is called a kidney cap. This is for people that are on kidney dialysis who have an arterial fistula, which is a hole where the dialysis machine plugs in. Sometimes it can rupture and can cause death. So this is just a very simple device that people can keep with them. If they get a rupture, they can use it, press it, and it stops the bleeding so that they can go get emergency help. It was 3D printed in Canada because we have an open source injection mold now in Poland. We are now injection molding them, which just means we can create more of them for a better cost. And yeah, this is one of a kind device. You know, again, empowering people to, you know, see where there might be a gap in the medical system and where we might be able to fill it. Gaza, our team there, they are still working 3D printers with solar panels, even in the chaos of the genocide right now. Before that genocide, they were running Stop the Bleed campaigns. We did have a goal to get a tourniquet in to every hospital, ambulance, and then every mosque and school, and then eventually every home. So that's a project that will continue when things calm down. During COVID, our Gaza team also acquired a $20,000 grant to distribute 3D printed face shields. So with that money, they also were able to get 10 Prusa printers and solar panels. And so, again, empowering a group. I gotta say though, based on the fact that we work in Gaza, we have a working team in Gaza, we are very enmeshed in the Muslim society in a way. All those people in our community that want to help out, that are donating or they want to help in some way, we're connecting with them. We're giving them hope. We're inspiring them to help in whatever way that they can. So I know I didn't follow my slideshow. You guys can see the slides. You can see how we manufacture stuff, mostly 3D printing. We do have injection molding now. The injection molds are made via CNC. I think there was some laser cutting, but that was maybe before my time with the face shields. We use as many types of low-cost manufacturing as we can. And, you know, as the cost comes down, it just becomes more accessible. The accessibility, though, in my mind, is not necessarily the cost of the tools or, you know, the materials that we use, that we try to make them as accessible as possible. It's the information, you know, having the information open and free online for anyone to use, comment on, share, and improve. That really is our biggest asset. It is the thing that we really do create. We create the devices, but we create also this open source community that is connecting with all of these other communities around the world. When you go online and you see Meet the Team, you can see that we have the Canada office, we have the Gaza office, we have the Poland office. We don't have a US office, but we work with so many people in the US helping us get FDA approval for the tourniquet. I mean, we're working on it. You know, there is a place in the States, DMDM, that has acquired that, I believe, and FDA approval for the kidney cap. Working with high school students, you know, that just want to do something. They just want to feel empowered. They just want to feel like they can give back and help. So we accept all help. And I think that makes GLIA what it is. And so this is This is how manufacturing is getting democratized. The price of the tools is coming down. People are connecting. Information is getting shared. There are no paywalls. There are no proprietary boundaries. We really are all in this together. I did believe that when COVID happened, and people were saying that. I know that that didn't really bloom into the rest of society, but it is true. It is true, and we take that to heart. We are all here as humans to help each other. You can see how equality does not equal equity. Equality is giving everybody the same thing. We're not about that. We're about equity, where we're giving what people need to bring them up to the same level. So here in the West, we're rich, we're privileged, we have everything that we need. But there are so many places in the world that are low resource that need more help, and we are here to do that. Another real great success story that I forgot to tell you about is Eric Lamery. He is amazing. He retired on a houseboat in Guatemala. He had a 3D printer. He saw a need in that community. He found our stethoscope online, free, open source. He started printing it. He's putting together medical kits now that include our stethoscope for these very rural medical clinics in Guatemala that have next to nothing. They have some bandages and some painkillers maybe. Not only is he printing our stethoscope for medical kits, he's doing prosthetics, upper limb prosthetics for these rural Guatemalans. And he just decided to do that on his own. He's connecting with the community. He's getting community buy-in by connecting with these people. I think that he also distributed our stethoscopes to some of the ambulances in his town, wherever he is in Guatemala. It's very rural. But yeah, another success story, another connection, and we have embraced him into our team. That's what it's all about. That's the democratization right there. People like Eric, people like Dr. Carey, people like Dr. Pierce, people who are connecting and sharing information to improve the world, really, with medical equipment that people need. We're making them gold standard. These are working as well as their counterparts. We are doing the research, we're getting the papers published, and yeah, I hope that you are all inspired as well to continue doing the work that you're doing. I'm inspired by this whole group and this conference, and unfortunately I couldn't be there due to weather. But yeah, I hope that everyone is inspired to continue working and continue working openly and sharing information and improving the devices that are being manufactured in order to bring the whole world up to a level where everybody has what they need, where healthcare is accessible and it's not only for the privileged or only for the rich. No way. We are all in this together. So thank you for listening to me. I think we're getting very close to the 30 minutes. Thank you very much for inviting me to the conference. I am grateful. I'm very privileged to be able to be a part of it. And yeah, I hope you liked what I had to say. So thanks everyone. Bye.
All right, everybody. So now we are heading into our afternoon, early evening portion. We thank you guys for staying with us so far today. And so the next speaker we have coming up is Alex Baldwin. So Alex Baldwin is an engineer and researcher in the bioelectronics space. Since 2023, he has been a part of USC's Center for Autonomic Recording and Stimulation System, also known as CARS, where he is helping develop a community around the open nerve open source implant. Please join us in welcoming Alex and his talk, Pursuing an Open Source Active Implantable Medical Device, Lessons from Open Nerve So Far.
Thanks a bunch, Yves. So like Yves mentioned, I'm part of a much larger group that's working on an open source device, an implant actually, for autonomic neuromodulation. We're headquartered at the USC with private partners MedAlly and Medipace. I'm going to start off the talk by talking a little bit about the challenges that we face as a very high-risk device, an active implant, and sort of at least where we sort of see the space for open source in the class 3 medical devices. Then I'll go a little bit into our project and the design choices we made to try to take advantage of the opportunities. So just to start at the very basics, every medical device has a lot of risks associated with it, obviously. There's things that could go wrong if a medical device breaks. There's things that go wrong if somebody designed it incorrectly or if it's manufactured incorrectly, manufactured by, say, a third party, or manufactured by even as simple as a technician who wasn't properly trained. And then, of course, there's plenty of things that could go wrong if the device is misused. And this could be somebody sort of intentionally misusing it, or like a hacker breaking cybersecurity, or even somebody who wasn't properly trained on it or didn't have proper instructions. Because of the high risks that are involved with medical devices, as I'm sure all of you know, almost every country has some sort of regulatory body that sets certain testing requirements and certain documentation requirements before they will allow these devices to be used in humans. I'm based in the US, as many of you are. In the US, the FDA is what controls this. And the FDA sort of sets different requirements based on risk classification in 3 levels, right? There's the relatively low risk devices, there's moderate risk, and then there's these class 3 high risk devices. I know that I would love to talk to many people. If any of you have experience in other regulatory systems, I wish Jen was here. I wanted to talk to her about the Canadian system. All right, I'm talking to you after this. But it is worth noting that the FDA system is there's reciprocity, and there's the ability for other countries, or I guess other countries have agreed to use these same classifications and accept these same tests. So you can see this is widely applicable to many other places in the world. Some examples of class 3 devices from the FDA include these following devices. So these would be devices that are life-sustaining. So if they're not working, then the person using them would die, something like a pacemaker. They also include devices that may kill or seriously harm a patient if the device malfunctions, or if it's not manufactured correctly, if it breaks somehow. Something like a coronary stent, where if it causes a thrombosis, that could present an immediate life risk. It also involves devices that are chronically implanted. So these are devices that might not necessarily be life-sustaining, but because they are complex and they're in the body for long periods of time, they have a lot of risks associated with them. This would be something like a cochlear implant, or like the open nerve device that we're developing. Now the FDA, and by the way, I am not at all a regulatory expert. So if anybody is, please feel free to correct me after this, or I'd just love to chat with you about this. But as an engineer, my understanding is that the FDA has a huge list of requirements that class 3 devices must go through before they ever get into humans. These start at the very start of the design stage, where design must be developed under a quality management system. There's a lot of documentation that goes into this, including risk and hazard analysis, thinking through every single risk and then designing in order to mitigate all of those risks. You have to have design inputs and have a very clear path between design inputs and design outputs. So you have to sort of know what you're designing before you even start and document the whole way. This lends to what the FDA recommends as a waterfall design, where you sort of start at the design, you go through this very clear linear process, and then at the end you lock the design before ever going into humans. Also, anything has to be manufactured under GMP, good manufacturing practices. This involves documenting and regulating who gets to manufacture the devices, making sure everybody's well trained, making sure everything's done repeatably and exactly the same way each time, and done in a facility that can document all of this and can be audited to make sure that it's compliant. Beyond the design stage, there's also a huge amount of requirements around benchtop testing. This includes things such as biocompatibility testing, making sure that nothing dangerous is leaching out of the device or that the materials won't interact with the body badly. It also involves, especially for our type of device, a lot of electrical testing, making sure that your device won't electromagnetically interfere with other things in the hospital, or making sure other things in the hospital won't interfere with it in a way that causes damage or could hurt the patient. And then there's the list goes on, but it goes down to even testing and validating the package you use, validating the labeling that you use. There's very specific standards behind labeling. And of course, testing and verifying sterilization and verifying the shelf life of the sterilization, making sure you can keep that if you've sterilized and manufactured something correctly and then put it on the shelf for 6 months, it still won't cause any new risks or increase any risks or any probabilities. Now, beyond that, after going through all of the benchtop studies and manufacturing correctly, you also have to do, in almost all cases, a safety study in animals. So for class 3 devices, it's, again, I'm not a regulatory expert, so feel free to tell me the exceptions to this rule. But as far as I know, it's almost always required to do safety studies in animals in order to show that the device is ready for human use and won't cause any harms or that there aren't any risks present that weren't identified during that benchtop write-up. After that, after going through all that, you're finally allowed to submit what's called an IDE, an investigational device exemption. And this IDE is for a specific limited clinical study. And basically you go back and forth with the FDA, tell them everything you've done. They usually give some feedback, ask for more information. And after all of that, you're allowed to finally use your device in a person for the first time. I think it's worth noting for an IDE, this only works for a single clinical study. This is very limited. You have to give the clinical plan up front. And even after this, you have to go through a lot more to use it again, right? You might need a new large animal study if, say, you're going to change the device configuration or use it for a slightly different indication. If you want widespread use, if you want doctors to just be able to prescribe this, you have to go through multiple clinical trials, usually a pilot trial, very small trial to show safety, and then a much, much larger trial to prove efficacy. Even after that, if you want a class 3 device to be used in the hospital, a lot of training and communicating with individual hospital surgeons, individual hospital systems has to be done. For most implants, doctors and surgeons will usually require some sort of technical support from the group designing the device in the OR so that they can show them how to use it, how to properly implant it, how to program it, things like that. The FDA also requires post-market surveillance, meaning that if anything goes wrong in a patient after the fact, you have to be constantly monitoring for this and then adjust those risk matrices in real time and make any design changes necessary to mitigate or ameliorate any new risks that might crop up. And then finally, you have to continue manufacturing these devices under a QMS, under GMP, and the FDA will regularly audit you and make sure that you're going through all the steps correctly and that there's nothing wrong with your system. So that is a lot. To sort of summarize what the FDA expects, and this is from a little bit of a philosophical perspective, but they expect centralized controlled development, right? They expect something where there's a linear progression between the design inputs and the design outputs. They also expect identical devices. So every device is made the same way, is made under the same process, is made under a way that's been tested and proven to be safe. They expect things to be done with a single indication, meaning a single disease, and a single device configuration. Again, regulatory people, tell me all the exceptions later, please. But as far as I understand, having a different indication for the same exact device or changing the configuration of your device a little bit, that is considered a brand new device under the FDA and requires new testing and new paperwork. And then finally, the FDA wants centralization and a consistent contact for audits and for recording those adverse events, making sure that the patients stay safe and that any sort of problems that crop up are addressed. At this point, I think it's worth noting the FDA is great. All my interactions with the FDA have been amazing, and the people there are incredibly helpful and will really work with you to understand these steps and to go through them. I've never had a bad interaction with FDA people. But it's important to note that they are focused on patient safety. And while they really try to get new technology to the clinic, their job and their mandate is to make sure that's done in a safe way. One of the results of all this is that development costs, especially for a class 3 medical device like we're developing, are incredibly high, right? This is from a 2022 study that tried to look at the average cost of developing a class 3 medical device in the US. And they found that before getting approval, the average cost was over, I think, $52–53 million. And if you look, $20 million was spent on average before ever getting to the first human, so the first study in people. Then there was a small amount of money for the pilot study, and the majority of that cost, over $30 million, for the pivotal clinical study. Obviously, for an open source group, this can look very prohibitive. I think that also something that I'm learning more about open source community and talking to all of you guys is I'm realizing there's also a little bit of a little bit of a tension between what the FDA sort of wants or what's required from a regulatory and a patient safety side, and like the ethos and the reason many people get into open source devices, right? Something that I've heard from a lot of you guys is that for open source, you value personalization, making sure everybody gets a device that meets their specific needs and is able to adjust that device, is able to adjust what they're doing to their own body, and has the freedom to sort of control what's happening to their body. I've heard that distributed manufacturing, whether that's each hospital having their own manufacturing or whether that's places, countries, or low-income locations that might not have big fancy facilities, that's something that is really a big push from open source. And like I mentioned just a second ago, empowering patients, letting them have control. As much as I think empowering patients and getting devices to market is a goal of the people at the FDA, since their focus is on safety, they and other regulatory bodies value things like control, repeatability, centralization, having one manufacturer to contact, having a rigorous process, and frankly, things that I think do conflict with the open source ethos that many of you have expressed, and also would do things like increase cost and sort of make it more difficult, especially for a high-risk device, to get to the market. So the question that I've been sort of struggling with, or the question that I've been asking myself as I am part of this Open Nerve project is there even a place for open source development for these high-risk medical devices, for these class 3 devices? And obviously I wouldn't be here if I didn't think the answer is yes. I do believe that there are a lot of problems with the existing sort of the way that class 3 devices go through that open source devices are uniquely able to solve. I'll go through a couple of these in a second, but I really do think that even though it is very difficult for an open source distributed group to get a class 3 device to the hospital, trying and really putting effort into creating these sort of open high-risk devices will help in a number of ways in both the patient side as well as for researchers and doctors that are trying to develop new therapies. The first and probably the most obvious way that I hope that open source medical devices will help is by lowering those development costs, right? Like the majority of the costs are taken up by the clinical trials, but there is a lot of money spent on just developing a new device and going through all of those processes before you ever get to first in human, even before you ever get to animal tests. I know from talking to a number of startups as well as working at a company of my own, not my company, being an employee at a startup in the past, millions of dollars can be spent redeveloping the same or very similar device before even going through all the testing plans or even doing animal studies. By reducing these costs and by even taking that chunk of the pie chart and shrinking it just a little bit, every little bit you shrink it, I believe leads to more patients getting therapies they need and lowers the barriers to groups such as nonprofits, academic startups, or even, academic groups, or even startups from entering the field and competing with those larger companies that are out there. Another place that I think open source can really help, especially in the class 3 medical devices, is in the case of abandoned devices. Now whole lectures could be written or could be spoken about abandoned devices. To summarize, this problem basically boils down to there are many, many devices that work that aren't commercially viable. And so either a large company will do a clinical trial, implant a lot of devices, and then decide it's not worth them pursuing, or maybe more commonly probably, a startup or an academic group will have great results on the clinical side, but just won't have the money to sustain themselves and will cease operation. We see this over and over again. I put 3 examples up here. One of them from my own backyard is the second sight artificial retina. This was a device that actually did gain FDA approval. This is an implant into the eye and then an external device that gives some rudimentary sight back. It was implanted in, I believe, about 450 patients. But after that, they weren't able to make money. And so they went out of business, and these patients were literally and figuratively left in the dark. So the device was still operating, and in some cases was absolutely life-changing and really improved their quality of life significantly. But if a part broke, especially like on the external device, how are they going to fix it? If there was a problem, if there was an infection, if there was an issue, how did they know the specs of that device or the risks or how to explant it safely, right? Many patients didn't even know if they could get an MRI. There's just no way of sort of helping these patients after this company went under. Another device that had a similar issue several years ago is the freehand system. This was for upper body paralysis. This was a functional electrical stimulation implant that allowed the patient to sort of directly stimulate muscles and gain some arm and hand movement back. This was a device that was also spun out into a startup. That startup went under, even though patients they loved the device. And I've actually met patients now 30 years later that are still using the device and benefiting from it every day. This, I'll give you sort of a preview of tomorrow. So this device actually has a happy ending in that researchers from Case Western University were able to sort of semi-legally acquire the IP back and continue supporting these devices. And this has actually evolved into what you'll see tomorrow as the Cosmic System, which my friend Chris Rexroth will present. So happy ending there, and one that's tying back into open source, luckily. And then another one sort of even more sort of connected to our project is the Brindley stimulator. This is a device that stimulates the sacral nerves for people with lower body paralysis to give back bladder, bowel, and sexual function. Really life-changing for so many people, but because it's not commercially viable, it's no longer manufactured. Replacement parts aren't manufactured. I know personally people that are trying to get this back, but it's a long road because everything's proprietary and the company just couldn't sustain itself. So one thing that I think there's several things that open source devices could do to help with this. And to be clear, this would be creating devices under an open source model that could then, if there is an issue on the commercial side, all the material would then be open source for others to help, to sustain, to perform maintenance on, and to maybe pick this up in the future. So some examples of ways that open source devices could help with this abandoned device problem include having the actual source files open could allow firmware and software updates, both to fix cybersecurity issues, new risks, or to update, for example, if you have a commercial cell phone as a controller, you need to have it work on a new cell phone, that needs a new software update. You could also be used to create replacement parts, whether that's 3D printing, CAD, or even electronics parts for the external devices. Stuff like open documentation, having those risk analysis out there, having the protocols live out there. That could allow future doctors to do surgery on these more safely, could allow more confidence around things like MRI safety. And it could allow new manufacturers to pick these up and continue selling a device they would still have to go through many processes with the FDA, but it would reduce that cost and it would lower the barrier to entry for re-bringing this device to the market. And then finally, one way that I think that open source could help with abandoned devices is by opening up protocols, whether that's communication protocols or say connector designs. This could allow parts to be replaced with equivalent parts with very minimal risk. For example, if you had a spinal cord stimulator and the battery ran out, you could potentially leave the leads inside, replace the actual pulse generator with a commercial one from a larger company, from a different company. And you could have confidence that those would interact correctly and that you could safely set the correct amount of stimulation. If you had those protocols and the design files and say the electrode designs, the electrode sizes, if all of that was open. So that's one way I think that open source could help. Another way I think open source could really help is in the preclinical side, right? I mentioned that almost all of these devices have to go through animal studies. actually one of the biggest sort of, if you look holistically at the development of class 3 medical devices in general, many of them fail at either the pilot study or at this preclinical side, because the devices just either don't work or aren't reliable in animal studies, or because those animal studies aren't able to translate to humans in a cost-effective way. One way that I think that open source devices could help is to allow to give a sort of a low cost and a low barrier of entry way of doing studies in animals with devices that could be easily translated to the clinic and that have been tested and gone through this rigorous process, and so are hopefully more reliable than some of the research devices that are currently used for animal studies. Or, for example, devices or boards that like an individual research lab would put together. They would have to go through that whole development process afterwards if they got good results. So this would hopefully skip them that step and save them millions of dollars, several years in getting this to market or to patients. And then finally, just going back to the cost thing, there are a lot of large companies that are able to sustain the cost of developing these expensive medical devices, but there's orders of magnitude more startups or small businesses that have brilliant ideas and might have some really good clinical or preclinical evidence that just aren't able to get to market. So I think having open source devices, whether as a device that companies can actually use and like conduct their studies with an open source device, or even having a reference design out there, having something out there that companies could look at and say like, oh, okay, this version works. Here's the schematic, here's the bill of materials, here's the CAD. I might need something slightly different, but I at least know something that works, and I know the pathway to getting to humans. I think this is really important, not just for lowering those barriers, but also for sort of bringing in people that aren't involved in the medical device world, or that maybe don't have connection to the FDA, haven't gone through this again. This lets them see the roadmap and see exactly what they need to do to be successful. All right, so that's a lot of very, I guess, theoretical stuff. I'm going to switch gears a little bit now and talk about our project. So, as I said, I'm part of a much larger project working on OpenNerve. OpenNerve is an open source implant for neuromodulation of the autonomic nervous system. I can't remember if I already said this, but autonomic nervous system, this means the nerves that aren't the brain and spinal cord. This would be nerves that go to things like the heart, the lungs, the liver, the pancreas, the intestines, nerves that control those sort of automatic functions of your body, the ones you don't have to think about. What we want to do is develop a whole system, a whole platform that consists of an IPG, an implantable pulse generator, and then a number of different sensors for biosignals, as well as electrodes to stimulate the body, and then allow people in the community to create new therapies using that platform, mixing and matching those sensors and those leads to what they need, and then going through all the preclinical and the clinical tests to actually get that new therapy to market. Oh, and again, I can't remember if I said this in the first slide, but we're a consortium. We're headed at the University of Southern California by Dr. Ellis Meng. But we also have two commercial partner, MedAlly, who is a contract manufacturer based out of South Carolina that does other medical devices, has a lot of great experience. And then MediPace, which is a startup based near Los Angeles that has actually gone through the process and has devices in humans before. And so they've both been incredibly helpful in sort of showing us the path and all the other stuff that needs to happen in terms of actually getting to market. There's many different components of OpenNerve. I can go over these later with you if you'd like, both on the established side that can be manufactured under QMS, as well as more research type devices that will give next generation capabilities. And we're currently in the stage of supporting a number of large animal studies by both academic partners and commercial partners that will hopefully be successful and then translate into human studies. We're also working on developing a stock of devices to make the path to market shorter, to get devices into people's hands quicker. And we're making development boards that are currently being manufactured for people in preclinical or who want to do benchtop studies. All of our source files are available on GitHub. I can go over all of these later with you guys if you want. But we're basically releasing things as we develop and releasing all of these under the Creative Commons CC BY open source license. So no share alike clause, all that's needed is attribution. So cite us. I know I don't have too much time left, so I'll skip ahead a bit. The next couple slides, I'm just going to go over a couple design choices that we as a group have made about OpenNerve that we think will hopefully enable those promises of Class 3 medical devices, or at least that's the intent. One of those design choices we made is to really lean into both modularity and compatibility with existing devices. I mentioned that there's a huge amount of leads being either sensors or electrodes that can plug into that central implantable pulse generator. We're trying to make those as swappable as possible, give people a huge amount of options to use, and then using things like splitters or interconnects allow any combination of leads to be used with the same IPG, allowing our one device to hopefully address many different therapies. We're also trying to keep it as compatible with existing standards as possible. This means using Bluetooth for communication instead of using a custom like mixed band standard. This means using ball seal connectors for our headers, even though anybody in here who knows probably hates ball seal, but they are the standard and they're used by commercial leads. So we're using the same size and the same connectors as say Boston Scientific's leads. So you could use a commercial lead with our IPG. We're also trying to keep as familiar a form factor as possible. As you can see, this looks very traditional-ish or something that a surgeon would look at and immediately know what to implant or how to implant it. We're also trying to increase device availability in a number of ways. We know that not everybody can build one of these from scratch. So we're working with our partner, who is the contract manufacturer, MedAlly, to both develop a stock of devices as well as to just be available for any sort of customization and be a contact point to sustain these devices if people do want to manufacture for a clinical study. On the other hand, we're also working on internally manufacturing a number of low-cost versions of these that can be distributed to people who just want to sort of get an intro to our platform and do initial development, firmware development, maybe small animal studies using it. We want to lower the barriers to entry as much as possible, and we're trying to not assume that people have the technical expertise to manufacture these on their own. Something that I won't go too into, but that we're just starting, will hopefully release in the future, is versions of firmware and software that are sort of safety locked, where we might have an API or we have a certain portion of the code that is, you can mess with it and modify it as much as you want, while having confidence that none of the core critical patient safety sort of portions or functions are touched. So this would allow hopefully flexibility and modularity while maintaining a lot of the patient safety. And then something that I think is a bit of a trade-off between the needs of the class 3 devices and the ethos of open source, but somewhere where we're trying to sort of stay in the middle and enable both, is just allowing groups to build proprietary therapies on top of our technology. So in order to get our open technology to clinical trials requires a lot of money, right? Even if we take that $20 million and we're able to shrink that down to like almost nothing, a pivotal clinical trial is still $30 million or, could be 30 million or more. In order to raise that money, venture capitalists or large firms, they want to see something proprietary. And so while we don't want to limit what we're doing, and we don't want to put any sort of barriers to people using our stuff, we do want groups to be able to build proprietary technology on top of our platform. This could be new firmware, this could be a special algorithm, or maybe a custom patented lead that plugs into our IPG. One of the reasons why we've chosen the CC-BY license is to enable that, right? We're not restricting, we're not doing a share-alike clause, and we're very much encouraging groups to take our open platform and do everything that they need to sustainably get that to the patients and get it into the clinic. And this includes sort of going private and creating closed source technology on top of it. Having said that, we really do want to encourage people to contribute back. And one of the things we're constantly looking for is groups that will contribute both the data that they're producing as well as any new designs back. We're lucky enough to have found several of those with our animal studies ongoing. Our goal right now, like I said, we're in early stages. So our goal right now is to get to our first in human and get to it in such a way that the communication with the FDA or the not necessarily clinical data generated, but the benchtop data generated in support of that can all be released as open source as well. Another thing that we'll be doing in the future is trying to grow our community and go from just being sort of designers and people that enable these researchers to having this back and forth between many different research groups that are actually developing on top of OpenNerve and improving the system. This is something I really liked Kara's talk about open source leg. We're definitely going to be inspired by that project as we move forward in the next year or so. Again, I know I'm out of time, so I just want to briefly say thank you to the many, many people involved in this. Alice Meng, who's been leading the project or originated it, all the groups at USC, MedAlly, Medipace. Our external advisory committee has actually been really great meeting with us and sort of showing us what is needed by the field. And then, of course, the NIH, who's really had this vision of funding open source implants before anybody, and funded this project and continues to support us to this day. So yeah, thank you very much. Feel free to come ask me any questions or reach out by email. All of our stuff's on GitHub, and I would love to talk to you about any of it. Also, as an academic, I'd be remiss if I didn't pitch our latest paper. So please come. I wrote a paper as part with our group about sort of kind of what I talked about, looking at open source devices and like what's actually needed to build sustainable open source devices. I pitched this kind of at people like me, medical device developers who aren't familiar with open source, but I'd love if you guys all checked it out and gave me any feedback you had. So yeah, thank you.
That concludes our speakers for today. Let's give them all a great big round of applause. So we at OSHWA are incredibly grateful for each and every one of you who took the time out of your busy schedules to attend this event. Building and fleshing out an open source ecosystem is no easy feat. It's very difficult, and it's really easy to forget that the work that we're doing is incredibly important, impactful, and needed, especially at this time of history. I also want to say thank you to the NSF grant for funding this, for making this opportunity possible for you all to come here and for us to host this. We've learned about some incredible projects and practices today, from ventilators to sharing for humanitarian aid to implantables. We're incredibly excited to be able to show you a few interactive examples. Next up, we will be heading to the demo table so you all can get a chance to see a few devices up close. You'll be able to see devices like Angelo, an assistive device for people dealing with hearing loss, devices from Cornell Tech's Maker Lab, and more. There will also be a zine table where you're all welcome to make mini magazines on open source healthware, what it means to you and what you wish others would know about it, and you're free to take them home and share them with your loved ones. My mom personally has no idea what I do for work, and I would love to take one to her. Yeah, so please take your personal items with you. Afterwards, we're going to have, I believe, some ice cream. Yeah, and we're going to take a walk to the smallpox hospital that's right down there. It's a very short stroll, and it's pretty cool. We'll be your unofficial, or the OSHWA team. If you can raise your hands, we will be your unofficial, very unofficial tour guides. But if anyone knows any Roosevelt facts, feel free to spit them out. Tomorrow we'll be meeting back in this room again. Registration will be at 8:30. Breakfast will be served. We'll be right back here. Please take your items with you once you leave this room. We'll be locking it behind us pretty much. And yeah, tomorrow, badges, make sure you have them. You will need them to get in. And I'm so glad to have you all here. We're really thankful. Demo tables are right outside. Ice cream will be out there too. And the walk will start around 5 o'clock. So thank you.